Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark. Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition, and a host of dwarf planets and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total, they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness, having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin, cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, the upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding. For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, and in civilizations as far-flung as Babylon, India, and China, Elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an 8th planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich Darest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer, hunted for this theoretical planet in the early 1900s driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death, the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the Sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials and initially not so different, they have since diverged into 4 dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the 4 inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns splashed across its dark grey terrain and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn-out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal, but a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees Celsius everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the Sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold onto a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe. but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation, especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the Sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the Sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth-like. All the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth. Its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In some, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds, a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the fifth planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, as pressure increases, hydrogen gas gradually becomes a supercritical fluid and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared, far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The four largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system. Its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark, cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics. A disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole, a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen-helium mixture in the upper layers and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Titan, is one of the most intriguing objects in the solar system. Titan is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Titan is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few % methane. For a long time, that smog hid Titan's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Titan has rivers, lakes and rain, but of liquid methane and ethane instead of water. At Titan's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Titan's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Titan, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Titan's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space. feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules. And it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers distance below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the seventh and eighth planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth-based telescopes and Hubble started seeing signs of weather: bright white cloud caps, dark spots, and streaky clouds. Uranus, it turns out, has a dynamic atmosphere that awakens when the Sun's heating is distributed more evenly. During the 2010s, astronomers observed some storms with ferocity comparable to Neptune's, including one huge storm in 2014 that was surprising given how far from the Sun Uranus is. Most of the time, though, Uranus is tranquil, looking, with gentle banding visible in enhanced images, and a serene aquamarine hue due to methane in its atmosphere, absorbing red light and reflecting blue, green. At cloud tops, Uranus is a frigid 215 degrees Celsius. Uranus also comes with rings and moons. It has a set of thin, dark rings made of radiation, darkened ice, and dust. They are narrow, kept in line by shepherd moons, and not nearly as showy as Saturn's, but they form a delicate series of hoops around the sideways planet. Uranus's moons include Titania, Oberon, Ariel, Umbriel, and Miranda. They are icy, cratered worlds, a few showing evidence of past internal activity. Miranda, for instance, displays one of the strangest surfaces in the solar system: patchwork regions of ridges and valleys next to older cratered terrain, and a cliff estimated at 20 kilometers high, a fall from which would take 15 minutes in Miranda's weak gravity. It's as if Miranda was shattered and reassembled, or underwent partial melting that froze in bizarre patterns. The larger moons have lesser quirks. Ariel has relatively few craters and signs of youthful resurfacing. Titania has giant canyons. Uranus's moons, like the planet, roll on their sides as they orbit E, which means, at solstices, one hemisphere of each moon is in continuous sunlight and the other in darkness. What seasonal effects that might cause on those frigid surfaces, we don't really know yet. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun, taking 165 years for one circuit. It's very similar to Uranus in size and composition, but Neptune is notably more active and more intense in color, a deep azure blue. Discovered in 1846 by mathematical prediction, Neptune was visited by Voyager 2 in 1989. Voyager 2 found a dynamic atmosphere, a great dark spot in the southern hemisphere and bright white clouds zipping around. Neptune's winds are the fastest in the solar system, up to 2,100 km/h, especially around those dark oval storms. The great dark spot seen in 1989 was a large high-pressure system exposing darker gases below, roughly the size of Earth, and it vanished a few years later. But other dark spots have since appeared and faded on Neptune. Unlike Jupiter's huge stable spot, Neptune's seem to be shorter, lived storms that come and go every decade or so. Neptune's upper atmosphere is about 200 degrees. Intriguingly, Neptune, like Jupiter and Saturn, radiates about 2.6 times more heat than it gets from the Sun, likely due to residual heat from formation. This internal energy might help drive the vigorous weather we see. Neptune's seasons last over 40 years. We haven't observed a full Neptunian season change yet, but in the decades since 1989 to the 2020s, we've seen some puzzling climate changes. The global temperature in Neptune's stratosphere actually dropped by about 7 degrees Celsius from 2003 to 2018. Then the South Pole suddenly warmed by 11 degrees from 2018 to 2020. It's a reminder that these far-off atmospheres can have variability we don't fully grasp yet. Neptune, too, has rings and moons. It sports faint rings with clumpy arcs. The outer Adam's ring has segments named Liberty, Equality, and Fraternity, where dust is clustered, for reasons initially mysterious until moonlets were found that shepherd those arcs. And Neptune's moon's number 14 at last count. The standout is Triton, Neptune's largest moon, which orbits backward relative to Neptune's rotation. Triton is a captured Kuiper belt object, likely snared by Neptune's gravity long ago. Triton is an ice world almost as big as our moon, with a young surface of frozen nitrogen, water ice, and weird cantaloupe terrain, and it is geologically active. Voyager 2 saw geysers on Triton, dark plumes of nitrogen gas and dust spraying up from the surface, carried by winds before falling. These are essentially cryovolcanoes driven by seasonal heating of Triton's south polar cap. Triton's thin atmosphere is about 1/70,000th Earth's pressure, but enough to have winds that bent those geyser plumes. Triton is extremely cold, yet it still has this slight atmosphere and active geysers, an astounding find. Triton likely has a subsurface ocean as well, kept liquid by residual internal heat or past tidal heating. Because of its retrograde orbit, Triton is slowly spiraling inward toward Neptune. Billions of years from now, it may either break apart into a spectacular ring or crash into Neptune. Neptune's other moons are much smaller and ice, rocky. Nereid has an extremely elongated orbit. Proteus is the second, largest, but still irregularly shaped. It's as large as an object can get without its gravity crushing it into a sphere. Proteus, dark and heavily cratered, might have avoided melting into a sphere by forming late, after the solar system calmed down. Tiny Hydra and Naiad and others zip around Neptune in closer orbits, some in complex resonant dances. Neptune's moon system likely lost whatever original satellites it had during Triton's capture. What we see now are either captured asteroids, comets, or fragments of an ancient moon system reassembled in new orbits. Thus, the outer solar system presents grandeur quite different from the inner. Here we have giant globes of gas and ice, lacking solid surfaces, but adorned with storms larger than Earth and delicate rings. We have an array of moons that are worlds in their own right, some sterile and cratered, others with subsurface oceans or thick atmospheres or erupting geysers. The giant planets act as architects and guardians of the solar system. Their gravity shaped the orbits of countless smaller bodies and may have steered water, rich comets toward the inner planets, possibly delivering Earth's oceans. Jupiter, especially, has shielded the inner solar system at times by vacuuming up comets, though it can also fling asteroids our way if they get too close. The giants likely migrated early on, scattering the debris disk and causing the late heavy bombardment that peppered the inner worlds with craters, and perhaps ejecting leftover planetesimals to form the distant Oort cloud of comets. As we leave Neptune behind, we pass into the realm of icy debris, the Kuiper Belt and beyond, where the sun's influence wanes. Yet even here we find worlds of consequence, the dwarf planets, which challenge how we define planethood and carry clues to the solar system's origin. Dwarf planets, worlds at the edge, and the definition of planethood. Far beyond Neptune's orbit, the solar system continues into a vast realm of icy bodies. Here, in the dim frontier, lies the Kuiper Belt, a broad ring of frozen remnants from the solar system's formation. Among these are several worlds large enough to be round, worlds that in another context might have been called planets. In fact, one of them was long honored as the 9th planet, Pluto. Today, we classify Pluto and similar bodies as dwarf planets, a category born from the realization that our cosmic neighborhood has more planets than we once thought, and that not all planets are equal in their orbital status. These distant dwarfs are small in size but rich in diversity, and they have forced us to confront the question, what does it truly mean to be a planet? Let us begin with Pluto, the iconic dwarf planet and former 9th planet. Discovered in 1930, Pluto orbits roughly 5.9 billion kilometers from the Sun on average, on a path that is highly inclined and elliptical. For 76 years, it was counted as the outermost planet, depicted as an icy oddball, until the early 21st century brought a paradigm shift. Pluto is about 2,377 kilometers in diameter, less than 20% of Earth's diameter, smaller than our moon. But what it lacks in size, Pluto makes up for in personality. In 2015, NASA's New Horizons spacecraft flew past Pluto and revealed an astonishingly complex world. Far from a simple cratered ice ball, Pluto displays a mosaic of terrains. Towering water, ice mountains rising 4,006 kilometers high, vast smooth plains of nitrogen ice with no craters, and dark reddish regions rich in organic molecules processed by sunlight. The most famous feature is Tombor Regio, nicknamed the heart of Pluto, a bright, heart-shaped area dominating one hemisphere. The left lobe of this heart, Sputnik Planitia, is a 1,000 km wide basin filled with nitrogen, carbon monoxide, and methane ices. This frozen plain is segmented into polygonal cells, evidence of convection. Pluto's interior heat causes the nitrogen ice to slowly overturn like a lava lamp, erasing craters and renewing the surface. It's a bit mind-boggling. Here is a tiny world at the solar system's edge, with active geology powered perhaps by the slow cooling of an internal ocean, or by exotic forms of heat transfer in the ice. Pluto's thin atmosphere is another surprise. When near perihelion, its surface ices sublimate, forming a tenuous atmosphere of nitrogen with a touch of methane. This atmosphere is about 100,000 times thinner than Earth's, but enough to form layers of delicate blue haze, as imaged by New Horizons when it looked back at Pluto, eclipsing the distant Sun. In Pluto's sky, the Sun is just a brilliant star, but it still drives a faint weather cycle. As Pluto recedes from the Sun, its atmosphere can partially freeze out onto the surface. New Horizons saw that Pluto's skies are layered with haze up to 200 kilometers altitude, and that the atmosphere is slowly escaping to space, forming a tail like a comet's. Standing on Pluto, you'd see a dim daylight with a charcoal-colored landscape, low gravity, and if you looked up, a thin bluish glow around the horizon from the atmospheric haze. Pluto doesn't wander alone. It has a system of 5 moons. The largest, Charon, is so big that Pluto and Charon Co. orbit each other around a point in space between them. Charon itself is a fascinating world. New Horizons showed it has a rugged surface with a massive equatorial canyon system far longer and deeper than the Grand Canyon, and a strangely bi-colored complexion. The northern polar region of Charon is reddish, likely stained by gases that escaped Pluto and froze onto Charon, then were altered by solar radiation into reddish tholins. The mutual orbit of Pluto and Charon is tidally locked. Each keeps the same face toward the other, waltzing through space as an inseparable pair. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier and irregularly shaped, probably captured or coalesced debris from the giant impact that created the Pluto-Charon system billions of years ago. Moving outward, we find Eris, the troublemaker that precipitated Pluto's demotion. Eris was discovered in 2005 by a team led by Mike Brown. It's an object currently slightly smaller in diameter than Pluto, but more massive by about 25%. Eris orbits the Sun on a highly eccentric path. When found, Eris was hailed in the media as the 10th planet, but its existence underscored that Pluto was not unique. Astronomers suspected many Pluto-sized objects awaited discovery. Eris was named after the Greek goddess of discord, fitting for the chaos it introduced into our understanding. It has one known moon, Dysnomia. Eris's surface is extremely bright. Its great distance means Eris is in deep freeze. If it comes closer, it might develop a thin atmosphere like Pluto's that refreezes when far out. Eris's discovery forced the IAU to formalize the definition of planet, and under that definition, Eris joined Pluto as a dwarf planet. But in terms of geology and interest, Eris is very much a planet, like world, simply one of a vast collection in the Kuiper belt. Besides Pluto and Eris, the IAU has so far recognized 3 other dwarf planets: Ceres, Haumea, and Makemake. Ceres is unique as the only dwarf planet located in the inner solar system, residing in the asteroid belt between Mars and Jupiter. In fact, Ceres was the first dwarf planet discovered and initially considered a planet until many more asteroids were found. Ceres is about 940 kilometers in diameter, roughly the size of Texas, and contains about a third of the mass of the entire asteroid belt. NASA's Dawn orbiter visited Ceres in 2015 and unveiled a cratered world that, while much smaller than Pluto or Eris, still shows signs of internal complexity. Most famously, Dawn spotted mysterious bright spots on Ceres, particularly in the crater Ocata. These bright patches turned out to be deposits of salts left behind by briny water that erupted or seeped to the surface, essentially cryovolcanic salt flats. This indicates that Ceres, even at its modest size, had a subsurface reservoir of salty water or mud that occasionally breaches the surface as a kind of ice volcano. One such cryovolcano on Ceres is Ahuna Mons, a solitary mountain likely formed by the extrusion of viscous, icy material that then hardened. Ceres likely differentiated into a rocky core and icy mantle. It may even hold a remnant subsurface ocean or pockets of liquid. Though cold and airless, Ceres surprises us by being a kind of geological bridge between the rocky inner worlds and the icy outer worlds. Back to the Kuiper belt, Makemake is another dwarf planet, slightly smaller than Pluto. Discovered in 2005, Makemake orbits at about 45 AU on a mildly tilted orbit. It has a very high reflectivity as well, with a surface of methane and ethane ices that give it a red-brown color. For a long time, Makemake was thought moonless, but in 2016, a tiny moon was found in Hubble images. Knowing its moon will allow us to determine Makemake's mass and density. Makemake has no known atmosphere, and its average surface temperature is around 240 degrees Celsius. Then there is Haumea, one of the strangest known dwarf planets. Discovered in 2004 and officially named in 2008 after the Hawaiian goddess of childbirth, Haumea is not spherical but rather ellipsoidal due to its incredibly rapid rotation. A day on Haumea is just under 4 hours. This fast spin elongated Haumea into a rugby ball shape. It's as if someone grabbed a ball of taffy and whirled it around. The centripetal force stretched it out. Haumea is also notable for its composition. It's largely water ice with a denser core, suggesting it might be the fragment of a larger body that collided and spun up. Supporting that, Haumea has 2 moons and is associated with a swarm of smaller Kuiper belt objects that share similar orbits and water-ice spectra, likely pieces of Haumea's shattered past self. In 2017, observers caught Haumea eclipsing a star and discovered it even has a ring, a 70-km wide ring of particles around its equator, likely in the plane of its fast rotation. Haumea's existence stretched our idea of a planet, showing that something can be round-ish and orbiting the sun, yet far from symmetric or solitary. Beyond these, dozens of other objects around the size threshold for dwarf planet likely exist. Quaoar has a moon and possibly a ring of its own. Sedna lurks on an 11,000-year orbit that takes it out to nearly 1,000 AU, possibly the first known member of the inner Oort cloud. The more we look, the more we find a continuum of worlds bridging planets and comets. The dwarf planets collectively highlight the continuum of planetary sizes and the gradations in the solar system's architecture. They forced the question, where do we draw the line between planet and smaller bodies? The 2006 IAU definition drew that line based on orbital dominance. By that rule, Pluto, Eris, Haumea, Makemake, and Ceres were reclassified because they share their space with many peers, but that definition remains debated. Some planetary scientists prefer a geophysical definition. If it's round by self-gravity, call it a planet, which would make dwarf planets planet in a broader sense. Others note that even Earth hasn't entirely cleared its orbit, but Earth so overwhelmingly outweighs them that the spirit of the definition holds. The public often still refers to Pluto as a planet out of affection. In truth, terms like planet are human categories we impose on nature's spectrum. Whether we call Pluto a planet or not doesn't change Pluto itself. With its glaciers of nitrogen, atmosphere that snows out, and potential subsurface ocean, Pluto defies any notion of being a static asteroid. We've learned that these so-called dwarfs can be just as complex and geologically active as the big planets. They are worlds by any meaningful measure. The classification is mainly about how they fit into the solar system's structure. Pluto hasn't cleared its orbit because it lives in a bustling disk of other icy bodies. That tells us about where and how it formed, but it doesn't diminish its status as a fascinating world. Indeed, studying dwarf planets like Pluto and Ceres has yielded huge insights. Ceres taught us that even small bodies can differentiate and possibly harbor liquid water or mud under the surface. Pluto showed that even in the far frozen reaches, geology goes on. Exotic ices can flow and convect like glaciers, and cryovolcanoes can build mountains. These bodies are time capsules from the solar system's formation and laboratories for processes at the extremes. They and their ilk likely delivered volatiles to the larger planets. And when we consider planets around other stars, many might be more akin to these intermediate worlds than to the 8 major planets we started out with. Having completed our grand tour of the solar system, from the sun, scorched rocks, to the gas leviathans and distant ice dwarfs, we can step back and summarize. Our solar system contains a family of worlds with a common origin but wildly divergent paths. Some went dry and airless, others drowned in thick atmospheres. Some stayed warm inside, churning and resurfacing. Others went cold and quiet. And around at least one modest star out of billions, one small rocky planet found a perfect balance and became alive. With this perspective, we now venture beyond the solar system to the planets that orbit distant suns. Here, we will apply what we've learned to understand how we detect these alien worlds, what types we've discovered, and what that means for the potential for life in the cosmos. Beyond our solar system, the exoplanet revolution. For thousands of years, humans wondered if the stars in the night sky had their own planets. In the last few decades, we found the answer, a resounding yes. We are living through a revolution in which exoplanets, planets around other stars, have gone from speculation to a catalogue of thousands. This discovery has expanded our concept of what a planet can be and placed our solar system in a galactic context. The first discoveries were surprising. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed exoplanets, and they were orbiting a pulsar. These were likely bizarre worlds that survived a supernova or coalesced from its aftermath. Not at all what we expected for the first planets beyond our solar system. Then, in 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, 51 Pegasi b, a planet at least half the mass of Jupiter, but orbiting so close to its star that its year is only about 4 days. This was a hot Jupiter, a kind of planet unknown in our solar system. It forced us to realize that planetary systems can be very different from ours. Since then, a torrent of discoveries has followed. Astronomers detect exoplanets mainly by two methods: the radial velocity method, which measures the star's subtle wobble due to an orbiting planet's gravity, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it. The Kepler Space Telescope stared at 150,000 stars and measured their brightness precisely, catching thousands of tiny dips that revealed over 2,600 confirmed exoplanets. These planets range from larger than Jupiter gas giants to smaller than Earth worlds. We learned that super-Earths and mini-Neptunes are extremely common, yet our solar system has none of those, implying our setup might be somewhat unusual. We found hot Jupiters, gas giants hugging their stars in scorchingly tight orbits, and hot Neptunes and warm Saturns, and more. We found multi-planet systems packed in close to their stars, some with planets in orbital resonances. We found circumbinary planets, planets orbiting two stars. We found free, floating planets by gravitational microlensing, rogue worlds that drift through the galaxy untethered to any star. And we found planets in the habitable zones of their stars, at distances where, if conditions are right, liquid water could exist on a rocky surface. One of the most exciting sets of discoveries was the TRAPPIST system. 7 Earth-sized planets orbiting a dim red dwarf star only 39 light-years away. 3 of these lie in the star's habitable zone. They are all tidally locked and crammed in a space that would fit well within Mercury's orbit. This system provides a tantalizing example of a very different kind of solar system architecture, one where a tiny star can have a retinue of Earth-size worlds potentially capable of retaining atmospheres. What are their surfaces like? Could any have water or life? Future telescopes like the James Webb Space Telescope are actually beginning to probe their atmospheres by analyzing starlight that filters through during transits. Exoplanets have shown us an astounding diversity of types. Hot Jupiters, gas giants orbiting extremely close to their stars. These have atmospheric temperatures of 1,000 pounds and 2,500 excites or more. Their atmospheres are puffed up by heat. Some are losing gas under the stellar radiation. They challenged our formation models. How did such big planets get there? We think they formed farther out and then migrated inward due to interactions with the protoplanetary disk or other planets. They taught us that migration can be a common process. Super-Earths. Planets a bit larger in radius or mass than Earth. Some may be rocky, others may have thick atmospheres. They might actually span a spectrum from big rocky planets to small gas planets. Not having one in our system means we had a gap in our understanding. Now we see they might be one of the most common types in the galaxy. A super-Earth might have higher gravity and retain a thick atmosphere or oceans for billions of years. Could they be even more clement for life than Earth? Or could they all turn into gas dwarfs with puffy atmospheres that make them uninhabitable? We're trying to find out by measuring their densities. Some super-Earths like 55 Cancri E are very dense, whereas others like Kepler 38d appear to have low density. Ice giants and sub-Neptunes. Many systems have planets in the 2 through 4 Earth radii range, akin to scaled down versions of Neptune and Uranus. These might have thick hydrogen, helium atmospheres on a rocky/icy core. Some could be more water-rich. The line between super-Earth and sub-Neptune might be around 1.6 thousand Earth radii. Intriguingly, Kepler data showed a dip in planet frequency around that size, suggesting many planets either have significant gas envelopes or have almost none. This phenomenon, the radius gap, likely reflects how planets either stop growing early and stay rocky or accumulate enough gas to puff up. The borderline worlds might have lost some atmosphere due to stellar radiation, ending up as rocky cores. Gas giants. Plenty of Jupiter, like or Saturn, like exoplanets have been found at various distances, some close, some at Earth, like distances, some far out. A few even orbit at Jupiter, like distances from Sun, like stars, implying their systems might have distant architectures vaguely resembling ours. We found giants in eccentric orbits. Some gas giants orbit binary star systems. We've even directly imaged a few young gas giants at wide separations. Rogue planets. Gravitational microlensing surveys have hinted that there may be numerous free-floating planets, perhaps ejected from forming systems or formed in isolation. Some estimates suggested they could be as numerous as stars or more, though recent data suggests not that common for Jupiter, mass ones. Still, it implies planet formation can be a turbulent process, with some worlds flung into the galaxy to wander alone. These would have no sunlight, just faint glow from leftover heat or radioactivity. A larger rogue could retain a thick atmosphere and maybe an internal ocean kept liquid by radiogenic heat or tidal heating from a prior moon, but life on such worlds would be a stretch. Exotic worlds. Some planets are simply weird, like lava worlds such as Corot 7b or Kepler 10b. Rocky planets so close to their stars that their surfaces are likely molten on the day side, with rock vapor atmospheres and mineral clouds that rain pebbles. Or ocean worlds that might be nearly all water by mass, essentially giant versions of Europa or Enceladus that grew larger. There's the idea of carbon planets around stars with different compositions, perhaps worlds where graphite and diamonds are abundant, or surfaces of carbide rock under tar, like skies. There are also puffy planets, gas giants with anomalously large radii for their mass, like WASP 17b, which is about half Jupiter's mass, but 1.7 times its size, and planets orbiting pulsars, or extremely metal, poor stars, or white dwarfs, each situation leading to unusual characteristics. When we compare these exoplanets to our solar system, we see that our system might not be typical in some respects. The absence of a super-Earth in our solar system is a puzzle. Perhaps Jupiter's formation prevented one from coalescing by scattering material. The lack of hot Jupiters in our system is a blessing for us. It appears that giant planets that migrate can disrupt inner systems heavily, whereas ones that stay put allow inner rocky planets to remain. Our relatively circular orbits and spaced-out configuration might not be the most common outcome. Many stars have multiple super-Earths in orbits closer than Mercury's, for example. Yet, among Sun-like stars specifically, some analyses suggest systems with a giant planet at Jupiter, like distance and small inner rocky planets, could be not extremely rare either. We're still trying to figure out how special our arrangement is. The significance of discovering exoplanets is profound. We now know that planet formation is a natural part of star formation. Planets are everywhere. The galaxy likely holds tens of billions of potentially habitable rocky worlds. We've taken the concept of planet from 5 wanderers in the sky to a cosmic norm. And each type of planet we find tests our theories. How do hot Jupiters form? Likely through disk migration or interactions. Why are super-Earths so common? Perhaps many systems form multiple mid-sized cores, which either become super-Earths or mini Neptunes, depending on how much gas they capture and how fast they migrate. What about Earth, like planets? Statistical studies from Kepler suggest perhaps 20–25% of Sun, like stars, have an Earth-size planet in the habitable zone. Around red dwarfs, potentially an even larger fraction have Earth-size planets in the habitable zone, as seen with TRAPPIST and others. However, red dwarfs are volatile. Their flares and long-lived activity might strip or sterilize those planets' atmospheres. The search is now shifting from finding exoplanets to characterizing them, measuring their masses and radii, detecting their atmospheres via spectroscopy, and even directly imaging some. We have detected atmospheric constituents on some exoplanets, sodium in hot Jupiter atmospheres, water vapor on some, even hints of things like titanium oxide, or possibly clouds of silicates or iron. In 2019, water vapor was detected in the atmosphere of a sub, Neptune, in its star's habitable zone, raising interest. The ultimate goal is to detect biosignatures, signs of life, in an exoplanet's atmosphere, such as oxygen or methane out of equilibrium, or other peculiar combinations that strongly suggest biology. That will require the next generation of telescopes and perhaps specialized space observatories with coronagraphs or star shades to directly see Earth, like planets next to their bright stars. The types of exoplanets we've discovered inform our quest for life. We've learned that terrestrial planets often come in families. A star might have several, some perhaps larger or smaller than Earth. We've seen that habitable zones around red dwarfs can host multiple tidally locked Earth-size worlds. Whether those can support life is an open question. Tidal locking means one side is always hot, the other cold. But if they have atmospheres or oceans, they could redistribute heat. We also consider how giant planets in a system might affect habitability. A Jupiter analog could help by diverting comets or hinder by destabilizing orbits. Our solar system's giant planets likely had a hand in delivering water, and also in preventing too many super-Earths from forming in the inner regions. In the context of habitability, the solar system offers 3 main candidates for life as we know it: Earth, Mars, and ocean moons. But none besides Earth have confirmed life. So as we look outward, we refine what conditions might be needed. Liquid water, certainly, is high on the list. A source of energy is needed. A stable environment over some billions of years might be necessary for complex life. Planets in the habitable zone of Sun, like stars, might be best situated for that. Red dwarf habitable zone planets get a lot of flares, especially in youth. Could life survive that? Possibly, if under ocean or ground, or protected by a magnetic field and thick atmosphere. We remain cautious, but hopeful. The future exploration of exoplanets is accelerating. The James Webb Space Telescope is already peering into some transiting planets' atmospheres with unprecedented detail. Upcoming missions like the Nancy Grace Roman Space Telescope will use microlensing to find rogue planets and cold planets further from stars, and test technologies for direct imaging. Further down the line, proposals for missions like LUVOIR or HABEX specifically aim to directly image Earth like planets around Sun, like stars, and search their spectra for biosignatures. On the ground, extremely large telescopes coming online in the late 2020s will be able to probe smaller exoplanets and perhaps take crude spectra of super-Earth atmospheres. It's conceivable that in the coming decades we might identify a planet where life could exist, or even find hints that it does exist, such as an atmosphere out of chemical equilibrium, strongly suggestive of biological activity. As our gaze extends to the stars, we carry the lessons of our solar system with us. We now know Earth is not alone as a potentially habitable world. There may be billions of Earths in our galaxy, but we also know habitability is fragile. Climate catastrophes like what befell Venus and Mars remind us that a planet's fate can change drastically. Earth has been lucky, but we must keep it that way. Life among the stars, the quest for habitability. When we talk about habitability, we usually mean conditions suitable for liquid water and life as we know it. From our study of planets, we've identified key factors. Distance from star. The concept of the habitable zone is crucial. Not too hot, not too cold for liquid water on the surface. For our Sun, that roughly spans from just beyond Venus's orbit to just beyond Mars's. For smaller, cooler stars, the habitable zone is much closer in. For bigger, hotter stars, it's farther out, but those stars live shorter lives. Atmosphere. A planet needs an atmosphere thick enough to create pressure for liquid water and to circulate heat, but not so thick as to induce a runaway greenhouse. Too thin, and water either freezes or boils away. The composition matters too. CO2 provides warmth, but too much can cook a planet. Some gases can be toxic to life. On Earth, life itself altered the atmosphere, creating the oxygen we breathe, which in turn allowed complex life. Magnetic field. As we discussed, a magnetic field can protect a planet's atmosphere from stellar winds. Earth's field likely helped us maintain our water and air over geologic time. Mars lost its field early, and then its atmosphere eroded away largely. Venus lacks a field, but its atmosphere is so thick that even with losses, it remains dense. Around active stars, a magnetic field could be even more critical to buffer the planet from high-energy radiation and flares. Internal heat and geology. Plate tectonics appears to help regulate climate via the carbon cycle on Earth. Volcanism also releases trapped gases and replenishes the atmosphere. A geologically dead planet might end up like the Moon. No atmosphere, cold interior, and static surface, not hospitable. Mars's waning volcanism might have doomed its climate. Venus's rampant volcanism may have contributed to its runaway greenhouse by belching massive CO2. A balance of geological activity is likely beneficial, enough to drive cycles and field generation, not so much as to create continuous global volcanism that might make a world too volatile for stable ecosystems. Stable climate and star output. A planet needs time for life to evolve. Earth has had liquid water for almost 4 billion years through various climate swings. A star's output can change. Earth's biosphere and geology compensated, keeping the planet habitable. If the changes were more extreme, or Earth's feedbacks weaker, life might have been snuffed out. So habitability is a combination of initial conditions and subsequent luck and balancing feedbacks. When we look at exoplanets, especially those in habitable zones, we assess these factors. Does the planet likely have an atmosphere? What's the star like? We've identified some promising potentially habitable exoplanets. Proxima Centauri, B. TRAPPIST, E, F, G, as mentioned. Earth-sized, in or near habitable zone around a dim star. Kepler, 452b, around a Sun-like star, often touted as older cousin of Earth, is larger, and the star is 6 billion years old. Interesting if it's rocky, but we're not sure it isn't too massive, having a thick atmosphere. Kepler, 2F and Kepler, 186 If, are smaller planets in their star's habitable zones, though their stars are a bit cooler than the Sun. Many others have been found by Kepler and TESS that are unconfirmed or with limited information. Ultimately, detecting life is the holy grail. What might be a sign of life? On Earth, the combination of abundant oxygen and methane is a strong biosignature. Seeing both would raise eyebrows. Also, things like the spectral edge of chlorophyll could be a signature if we ever got a direct color spectrum of an exoplanet's surface. Even seasonal changes in atmospheric composition could hint at biology. It's tricky because we have only one example of life's impact on a planet, Earth, and alien life might produce different gases. Also, non-biological processes can sometimes mimic biosignatures. So context is everything. We'd need to understand the planet's star, history, and environment to interpret signals, while the exoplanet hunt proceeds mostly via remote sensing. In our own solar system, we can go to these worlds to search for life or conditions. Mars is currently being combed by rovers and orbiters. Europa and Enceladus are top targets. Europa Clipper will orbit Jupiter and repeatedly fly by Europa to map its ice and composition, even scouting for plumes to sample for organic molecules. JUICE will explore Jupiter's moons and eventually orbit Ganymede, studying its ocean and magnetic field. For Enceladus, a future mission concept aims to directly sample its geysers for biomolecules and maybe even signs of microbial life. Titan will be visited by Dragonfly, a flying drone like Lander that will hop across Titan's dunescapes to drill into organics and look for prebiotic chemistry or even life's handiwork. Thus, our exploration strategy is twofold. Within our solar system, investigate all potentially habitable niches. Beyond our solar system, improve our telescopes to identify promising Earth, like planets around nearby stars, and eventually directly image them. We stand at a moment in history where we can, for the first time, meaningfully search for life beyond Earth. Not long ago, planets around other stars was still hypothetical. Now it's routine science. The next leap, finding evidence of life's effects on another world, would be profound. It would tell us whether life is a cosmic common occurrence or a rare fluke. Either answer is deeply significant. If common, the universe may be teeming with biology and perhaps intelligence. If rare, then our pale blue dot is an even more precious oasis in a vast, perhaps mostly sterile desert. Future frontiers, exploring new worlds, and the fate of our planetary journey. What does the future hold for planet exploration? Both in continuing to explore our solar system and in reaching for others, the coming decades promise to be exciting. Within the solar system, several ambitious missions are on the horizon or in progress. We mentioned Europa Clipper and Dragonfly. These will illuminate the potential habitability of ocean worlds. Mars exploration continues. After Perseverance collects samples, a multi-part Mars sample return mission by NASA ESA aims to bring those samples to Earth by the mid-2030s, allowing labs on Earth to scrutinize Martian soil for signs of ancient life with far greater precision than any rover could. Plans for human missions to Mars loom on the multi-decade timescale. The 2030s or 2040s may see the first footsteps on Mars, fulfilling a dream long imagined. Humans could conduct science on Mars that robots struggle with, though robots will likely have already answered the life question by then. At Jupiter and Saturn, the next generation might be missions to actually land or sail in the oceans of the moons. A concept being studied is a Europa lander to drill through a thinner part of the ice, or a penetrator that melts its way down. Even more fanciful is a submarine for Titan's methane seas or an Enceladus ice drilling lander. These are technologically challenging, but so was landing humans on the moon. It's a matter of will and priority. There's also renewed interest in Venus. After decades focusing on Mars, NASA and ESA have recently approved missions to Venus in the 2030s, Da Vinci Plus and Veritas. ESA's Envision orbiter is planned as well. These missions will give Venus a fresh look, important for understanding how Earth, like planets, diverge. If Venus was once more temperate, when and how did it turn so hostile? We might find clues of past water or ongoing volcanic gases. Farther out, Uranus and Neptune remain the only major planets not revisited since Voyager. The US Planetary Science Decadal Survey has prioritized a Uranus orbiter and probe mission for the 2030s. This mission would journey for around 15 years to Uranus, deploy an atmospheric entry probe to sample Uranus's air directly, and orbit Uranus for a few years to study its rings, magnetosphere, and moons. Such a mission would be a bonanza of science. Understanding ice giants will fill a gap in our knowledge of planet formation. After Uranus, Neptune is a logical next target, potentially in the 2040s, possibly with a Triton lander or ocean finder included. These missions, though far off, underscore humanity's commitment to exploring all corners of our solar neighborhood. In the realm of exoplanets, as discussed, new space telescopes like JWST are opening windows. JWST has already begun examining atmospheres of some transiting exoplanets and even directly imaged a couple of gas giants. Over its lifetime, it might be able to probe some super-Earth atmospheres around nearer stars for molecules like water or CO2. The Roman telescope will find many cold exoplanets via microlensing and carry a technology demonstrator coronagraph to directly image a handful of known giant exoplanets, sharpening our skills. By the 2030s or 2040s, we hope to launch a large segmented mirror telescope. Such a telescope, armed with a coronagraph or a starshade, could directly see Earth-sized planets around perhaps dozens of nearby sun, like stars, and take spectra of them, searching for biosignature gases. Imagine seeing a pale blue dot in the sky of another star and detecting, say, oxygen, or even a color variation due to continents and oceans. That would be a civilization, changing discovery. We stand perhaps a generation away from that possibility. There are also imaginative projects like Breakthrough Starshot, which envisions sending gram-sized microprobes to Alpha Centauri using powerful laser sails, reaching 20% the speed of light to get there in about 20 years. While highly experimental, if such technology matured, we could potentially have flyby images of planets around the nearest stars within our lifetimes, perhaps revealing continents or clouds on an alien Earth. It sounds like sci-fi, but no more so than Jules Verne's moon rockets did in the 1860s. Human curiosity drives innovation, and the payoff, touching another star system, would be historic. As we explore, we also reflect. All these worlds we've visited in our minds, from Mercury's battered ground to Neptune's windy blues, have taught us about diversity and commonality. Diversity in that each planet is its own world with unique quirks. Commonality in that they are all part of one grand physical system, obeying the same gravity and chemistry, following similar stages of formation and evolution with variations on the theme. We've seen parallels: volcanoes on Earth and Io, sand dunes on Mars and Titan, polar lights on Earth and Jupiter, ice crusts on Europa, and our own Arctic Ocean. We've seen cautionary tales, a planet almost our twin that became a furnace, a small world that lost its shield and dried out. We look back at Earth with new appreciation for its perfectly tuned conditions, not too hot like Venus, not too cold like early Mars, big enough to hold air, spinning fast enough to have a magnetic field, blanketed by life that in turn helps maintain stability. The study of planets has also put us in our place. Copernicus removed Earth from the center. Galileo showed Earth is just one of many bodies. The last century revealed that even the sun is one of billions, and now that planets abound everywhere, our home is just one island in a vast archipelago of worlds. And yet, to us, it's special, the only known cradle of life. As we search for life elsewhere, we can't help but wonder about the rarity or ubiquity of life. Will we find biosignatures on Mars or Enceladus or an exoplanet? If we do, it means life might sprout wherever conditions allow, implying a living cosmos with many neighbors. If we don't, it could mean life is a freak accident, a cosmic miracle unique to Earth. In that case, the responsibility on us as stewards of the only garden of life increases immeasurably. Either way, studying planets has given us a cosmic perspective. Carl Sagan's famous pale blue dot speech encapsulated it. All of human history played out on a mote of dust suspended in a sunbeam. Every planet we visit reminds us of the fragility of habitability, how thin an atmosphere is, how delicate a balanced climate can be. We see Venus and fear a runaway greenhouse. We see Mars and fear the loss of a magnetic field and atmosphere. We turn those lessons to our own situation, recognizing our planet's climate is not static, that pumping greenhouse gases can push Earth toward a new, possibly unfavorable state. The barren surfaces of Venus and Mars urge us to be careful lest Earth follow their paths in some distant future by our own doing. Planets also teach resilience and change. Earth has gone through mass extinctions and recovered. Life has a tenacity. Who knows, maybe life exists in some form under the ice of Europa or in Titan's chemical stew, very different from Earth's biology. If we find even a second Genesis in our solar system, it means life is a cosmic imperative. If we don't find it nearby, we'll keep looking outward. Ultimately, the exploration of planets is a human story of curiosity, wonder, and reflection. We have gone from gazing at wandering stars to sending robot emissaries across the void to stand on those worlds and report back. With each step, we've been awed. We felt the volcanic heat of Io and shivered in the methane rain of Titan. We marveled at Saturn's rings, countless icy particles orchestrated by gravity into one of nature's most gorgeous sights. We flew through a geyser on Enceladus and tasted primordial water. We watched a sunset on Mars through the eyes of rovers, its sky tinged butterscotch by fine dust. These experiences, albeit through our mechanical proxies, have enriched our soul and expanded our imagination of what worlds are out there. Looking up at the night sky now, we no longer see just pinpoints of light. We see other suns with their own planets, perhaps a giant with storms bigger than Earth, or a warm ocean world enveloped in clouds, or a rocky orb struggling to hold on to an atmosphere. We might even see lights of another civilization, though none have been detected yet. The possibility is there, made real by the sheer number of planets. So we end our journey where we began, under the stars. But now, when we point out the wanderers, our neighboring planets, we do so with understanding and kinship. The word planet means wanderer, but ironically, planets also taught us how connected everything is. Wanderers though they are, they orbit in a family, influencing each other and their star. And we, wanderers ourselves, have begun to venture from our home to visit them, first with our eyes, then with our ships, someday perhaps in person. The story of planets is the story of cosmic islands and the voyages between them. It's a tale of creation, how dust can clump and ignite and then leave residue that becomes worlds both barren and lush. It's a tale of destruction and renewal, giant impacts that can destroy worlds or birth moons, atmospheres that can collapse or run wild, but also life that can emerge and transform a whole planet. It's a story that forces us to ask, how common is a world like ours? How rare are we? And where do we go from here? In the next decades, we may finally get an answer to, are we alone? By detecting life signs elsewhere. Or we may find that Earth is singular so far. In either case, planet exploration will continue, driven by the deepest human urges to know and to go. Unmanned or manned, we will likely set foot on Mars, dive into the seas of Europa with submersibles, maybe float in the atmosphere of Titan or Venus in balloons. We will refine our techniques to image Earth like exoplanets. Perhaps one day, far in the future, our descendants will build starships to visit neighboring systems, turning those points of light into landscapes beneath their boots. As our perspective broadens, our appreciation of Earth deepens. The pale blue dot that Sagan spoke of is our only home in a vast cosmos, at least for now. The other planets show starkly that Earth's hospitality is unique in our solar system. So exploring other planets is not just about them, but also about us, holding a mirror to Earth. We see what happens when greenhouse gases go unchecked, or when a small planet cools and dries, or how a protective magnetic field can preserve a world. These lessons are invaluable as we manage Earth's future. Finally, there is an almost spiritual aspect. By understanding planets, we come to understand our place in the universe. No longer are we the center, we are part of something vast and magnificent. The diversity of worlds out there suggests that if life could arise here, it could arise elsewhere. And if it hasn't elsewhere, then we carry an enormous responsibility as the sole known bearers of consciousness to care for our oasis and perhaps spread life beyond it. We began this journey with the ancient wanderers in the sky. Now, having explored the fire of the inner planets, the grandeur of the giants, the ice of the dwarfs, and even peered to the worlds of other stars, we end with a renewed sense of wonder. The night sky will never look the same. Each dot is a sun, many with planets, some perhaps with beings looking back at a tiny sun pinprick that is our home. The voyage of planetary exploration has really just begun. There are new horizons to reach, literally, as with the probe New Horizons at Pluto, and profound questions still to answer. But one thing is certain: our curiosity will not cease. We will continue to wander, in person or by proxy, mind and body, outward to the planets and beyond. For in seeking these other worlds, we ultimately seek to know ourselves and our place in the cosmos. It is a grand story, one that spans from the fires of creation to the potential spark of life, and it's a story with no end in sight. Each planet we visited, by telescope or spacecraft, has left us changed. They have shown us beauty beyond measure, forces beyond fear, and resilience beyond expectation. In their extremes we find meaning. Mercury's day, night cycle, whispering that too much heat and too little air yields desolation. Venus's clouds warning how quickly paradise can be lost. Mars's dry rivers reminding that climate can turn on a planet. Jupiter's storms humbling us with their power. Saturn's rings teaching the elegance of gravity's order. Uranus and Neptune revealing that even on the edge of darkness, winds still dance. Pluto and its kin proving that even small worlds can be geologically alive. As we continue to learn, we should also take a moment to feel the awe. We are fortunate to live in a time when the long-lost siblings of Earth have been revealed in all their glory. A human from just 100 years ago could only dream of what we've seen. And a human 100 years from now might walk on Mars or float in a Europa submersible, living our present dreams. Our quest for knowledge and exploration binds the generations in a common continuum of discovery. So, step outside on a clear night. Find Venus blazing in the west or Jupiter rising in the east. Know that you're looking at entire worlds, places that we've now touched with our robotic emissaries and, one day, might touch with our hands. The sky that was once the realm of gods and myth is now open to us as a realm of nature to explore. The wanderers are no longer distant mysteries. They are destinations. They have become real places with landscapes and weather and histories we can narrate. And in exploring them, we've woven their stories into our own. We too are wanderers. As Sagan said, we began as wanderers, and we are wanderers still. We have lingered long on the shores of the cosmic ocean, but now we are setting sail among the stars. In the end, the study of planets teaches us humility and unity. All those worlds out there, and here we are, one small crew on spaceship Earth, sailing together through space and time. The pale lights of Mercury, Venus, Mars, Jupiter, and Saturn in our sky are like signposts, telling us where we've been and where we will go. When we finally decipher the secrets of alien atmospheres or find microbes on a distant moon, it will underscore that we are a part of this universe, connected to the planets and stars around us. We are not apart from nature. We are born of the same processes that birthed the planets. The voyage will continue. New rockets, new telescopes, new generations of scientists and explorers will carry the torch. They'll answer questions we haven't thought to ask, and surely encounter surprises we haven't imagined. Planets will continue to fill us with wonder, whether it's weird new exoplanet types or hidden oceans discovered under icy crusts. Each answer will likely raise more questions, as is the way of science. But that is a joy, not a frustration. It means the adventure of discovery is endless. There will always be another horizon, another world to learn from. And as long as humans have eyes to the sky and minds that dream, we will be out there, exploring, moving outward, one world at a time, forging connections across the darkness. In a sense, by exploring the planets, we are the universe exploring itself. Matter that became life, life that became intelligent, now reaching back out to understand the grand mechanism that produced us. Every footprint left on the moon, every photon counted from a distant exoplanet, is the cosmos coming to know itself through us. Our journey through the planets has thus been a journey inward as well, into the nature of who we are and what we may become. When future explorers stand on Mars and look up at a sky with 2 moons, or when a robotic probe sends back the first images from an Earth, like planet light years away, the sense of connection will only grow stronger. We'll realize ever more that we share the universe with all these worlds, and maybe share it with other life. For now, we cherish our pale blue dot while reaching for others. We end our tour back on Earth, gazing up, but with new eyes. The wanderers in the sky are no longer distant gods, but places we know. Siblings in the solar family, each unique, all kin. We have walked among them in our imaginations and through our proxies. Soon, we will with our own feet. The story of planets is ultimately a celebration of human curiosity. We dared to ask ancient lights what they were, and we answered, revealing a universe richer than our ancestors could have believed. Stand under the night sky and feel that connection, tiny though we are. We understand those points of light now. Mercury, Venus, Mars, Jupiter, Saturn. We know them intimately. And far beyond, around myriad stars, countless other planets circle, waiting for our discovery. The wanderers will guide us outward, and wherever we go, we will carry the legacy of understanding forged here at home. In that sense, the journey of exploring planets is a journey of self-discovery for humanity. We set out to find new worlds, and in the process, we found ourselves, one people on one world, learning that the cosmos is full of worlds. It is perhaps the grandest revelation of all. The planets have taught us that the only borders are those we create ourselves. In the cosmos, all worlds share the same sky. The wanderers still move across the heavens as they did for the ancients. But now, when we see them, we greet them as familiar friends, places we've been or soon will go. And as we trace their paths and even send our emissaries to dance among them, we too become wanderers beyond the earth, united in the eternal quest to know the universe and our place within it. The story of planets, our story, continues, onward and outward, under the cosmic sky that we all share. In the silent depths of space, a star is dying. After millions of years of shining, pouring light and warmth into its corner of the galaxy, the star's final moment has arrived. It happens in an instant. The star's core collapses, and then, boom! A titanic explosion tears the star apart from within. Brilliant light floods the darkness. For a few blinding weeks, this single dying star outshines the billions of other stars in its galaxy. Its outer layers are hurled into the void, carrying a treasure of newly forged elements. In the aftermath, a glowing cloud of stellar debris, rich with hues of neon blues and fiery reds, laced with specks of gold, expands outward, and at its center, a strange new object is born from the star's crushed heart. This is a supernova, the spectacular death of a star. It is both an ending and a beginning, a cosmic death and rebirth wrapped into one event. Supernovae are the universe's great paradox. They are violent, destructive events, the most powerful explosions since the Big Bang. Yet from their chaos comes creation. When a massive star dies in a supernova, it doesn't vanish without a legacy. The brilliant blast is a final act that seeds the cosmos with matter that will become new stars, new planets, perhaps even new life. In a very literal sense, our own existence is connected to these explosions in the sky. Every atom of calcium in our bones, of iron in our blood, of oxygen that we breathe, was forged in the cores of stars and cast across space by supernova explosions. The universe recycles itself through these stellar deaths. In the ashes of dead stars lie the ingredients of future worlds. To understand how such an immense explosion happens, we must first understand the life of a star. Like living creatures, stars have life cycles. They are born, they age, and they die. A star's fate, the way it dies and what it leaves behind, depends on its mass, the amount of matter it contains. Small stars live long, steady lives and perish quietly. Very large stars live short, furious lives and die in cataclysmic blasts. Imagine a stellar nursery, a cold, dark cloud of gas and dust in space. Over time, gravity draws parts of this cloud together into clumps. One clump grows denser and hotter at its core until a new star ignites, shining with nuclear fire. This infant star spends most of its life steadily fusing hydrogen into helium in its core, a process that releases the light and heat we see from stars. For a star of modest size, like our Sun, this phase lasts billions of years. Eventually, the star depletes the hydrogen at its center. No longer able to produce the same energy, the core begins to contract under gravity. The star's internal furnace seeks new fuel. It raises the core temperature until helium, the ash of the previous stage, can fuse into carbon and oxygen. The star's outer layers swell enormously and cool as this happens, and the star becomes a red giant, hundreds of times larger than before. Our Sun will follow this gentle path. About 5 billion years from now, it will expand into a red giant, likely swallowing Mercury and Venus and turning Earth into a scorched ember. The Sun's light will turn bloody red, and its size will loom vast in the sky. But the Sun is not destined to explode as a supernova. It simply isn't massive enough. After it has fused helium into carbon and oxygen, it will shed its outer layers into space, creating a glowing planetary nebula, a shell of colorful gas expanding away into the darkness. Ultimately, the Sun's core will be left behind as a small, hot, white dwarf about the size of Earth. It will glow faintly with residual heat for billions of years, slowly cooling and dimming. That will be the Sun's quiet end, a final cosmic whisper rather than a shout. But for stars significantly more massive than the Sun, the story plays out quite differently. A star, perhaps 10 or 20 times the Sun's mass, lives fast and dies young. These massive stars burn through their nuclear fuel at a prodigious rate. Live fast, die young could describe them. They shine tens of thousands or even hundreds of thousands of times brighter than the Sun, but exhaust their core fuel in only a few million years. As a massive star ages, it undergoes a vivid transformation. After burning through its core hydrogen, it becomes a red supergiant, much like the famous star Betelgeuse in Orion's shoulder, a colossal swollen star so large that if it replaced our Sun, its surface might extend beyond the orbit of Mars. Inside its core, the star is a raging furnace, fusing heavier and heavier elements in successive stages. Hydrogen fuses to helium. Helium fuses to carbon and oxygen. Carbon fuses into neon, sodium and magnesium. Neon burns to oxygen and magnesium. Oxygen fuses into silicon and sulfur. And, finally, silicon fuses into iron and nickel. In the star's final days, its interior resembles a giant onion, with layered shells of different elements. Each shell the burning ash of the previous fuel, nested one inside another. Then the star reaches a fatal threshold: iron. When iron accumulates in the core, the star has run out of road. Fusing iron doesn't release energy, it consumes energy. The mighty engine at the star's center, which for millions of years has fought against gravity by pumping out heat and pressure, suddenly falters. With no new energy to support it, the iron core is overwhelmed by the star's immense weight. In a fraction of a second, the core implodes. The inner core, once perhaps the size of Earth, collapses to something only a dozen kilometers across. At the immense densities achieved, protons and electrons in the core smash together and merge into neutrons. The core, now essentially a ball of neutrons, is as dense as an atomic nucleus. The collapse is so violent that temperatures spike to billions of degrees. A flood of neutrinos, ghost-like subatomic particles, pours out of the core, carrying away a tremendous amount of energy. For a moment, it seems as if the entire star might simply disappear into itself. But when the core's collapse is finally halted, something extraordinary happens. The imploding core bounces outward, sending a shockwave racing back up through the infalling layers of the star. Those trillions of neutrinos streaming out also deposit energy into the surrounding matter. Within milliseconds, the rebounding shockwave is energized and blasts outward through the star's layers. The star's outer regions, which have been rushing inward, now are violently blown outward at incredible speeds. The energy released is staggeringly large, comparable to the total energy the sun will radiate over its entire 10 billion-year lifetime, unleashed in a single burst lasting only a few seconds. The star has become a supernova. If you could stand on a hypothetical planet orbiting such a star, the experience would defy imagination. In the days leading up to the explosion, you might see your sun swelling into a red giant, its color deepening to a dusky crimson, its light fading and flickering as it sheds its outer layers. The sky might glow strangely as the star ejects shells of gas. Then, seemingly without warning, the end comes. One moment, the night side of your planet is dark and serene, the bloated red sun hanging low on the horizon. The next moment, a blinding flash ignites the sky, as if 1,000 full moons have risen at once. The star erupts with ferocity unimaginable, outshining entire constellations. In seconds, a wave of intense radiation scorches the planet's surface. The atmosphere itself might ignite in a brief, furious glow. Within minutes, the crushing blast front arrives, a wall of plasma and gas moving at millions of kilometers per hour. If the planet is close enough, it would be stripped of its atmosphere and perhaps shattered entirely. It is a celestial cataclysm beyond comprehension. Thankfully, we observe supernovae from the safety of tens of thousands of light years away, where their violence translates only into a wondrous light show in the sky and a rain of subatomic particles that pass harmlessly through us. From hundreds or thousands of light years away, a supernova appears as a sudden new star that wasn't there before, often outshining all the normal stars around it. It can start as an unremarkable pinprick one night, and then, night after night, grow in brightness until it rivals the brightest stars, or even the moon in the sky. For weeks, sometimes months, it remains brilliant, visible even in daylight if it's close enough, and then gradually it fades, shrinking back into the darkness as its energy is expended. Eventually, it disappears from casual view entirely, leaving behind only the expanding cloud of debris visible to telescopes and, at the center, a strange new stellar remnant marking the place where the star's heart was. Not all supernovae, however, come from the core, collapse of a massive star. There is another pathway to these cosmic explosions, one that involves a kind of star that has already died once. When a star like the Sun dies, as we said, it leaves behind a dense core called a white dwarf. A white dwarf is extremely dense. Imagine packing the Sun's mass into a sphere the size of the Earth, and it's made mostly of carbon and oxygen, the ash of the Sun's core fusion. Normally, a white dwarf simply cools and fades over eternity, but in a close binary star system, a white dwarf can get a second chance at a dramatic exit. If the white dwarf orbits a companion star, the white dwarf's intense gravity may begin stealing gas from its partner, siphoning matter onto itself. Over time, the white dwarf grows heavier. As it gains mass, it grows more and more compressed, and its core temperature climbs. If the white dwarf approaches about 1.4 times the mass of our Sun, the pressure and temperature at its center becomes so high that carbon fusion ignites explosively throughout the star all at once. The white dwarf, in effect, becomes a gigantic nuclear bomb. In a fraction of a second, a thermonuclear chain reaction races through the dwarf star's carbon and oxygen interior, unleashing an atomic inferno that blasts the white dwarf to bits. The star is completely destroyed in a furious thermonuclear supernova. In some cases, two white dwarfs in a binary system can also spiral into each other and merge, likewise igniting a catastrophic supernova without needing gas from a normal star. Different route, same destination, an explosion. Astronomers classify supernovae based on the light they emit, especially the fingerprints of elements seen in their spectrum. The first big distinction is simple. Does the supernova's spectrum show hydrogen or not? Hydrogen, the most common element, usually makes up the outer layers of stars. A supernova that clearly shows hydrogen in its ejected material is called a Type II supernova. These are typically the core collapse explosions of massive stars that retain their hydrogen envelopes right up to the moment of death. Other supernovae show little or no hydrogen in their spectra. These are generally called Type I. The white dwarf explosions in binary systems are one subtype of Type I, specifically Type Ia supernovae. They have a distinctive spectral signature. No hydrogen lines at all, but a strong absorption line of ionized silicon, plus later an emergence of ion lines. These indicate the presence of elements like silicon and iron synthesized in the explosion. Type Ia supernovae, being born of similar white dwarf trigger conditions, also reach almost the same peak brightness, which made them incredibly useful, as we'll see later. There are also types Ib and Ik, which, like Type II, are core, collapse explosions of massive stars. But in these cases, the star had lost its outer hydrogen layers before it exploded. Such stars might shed their outer layers through powerful stellar winds, or by transferring mass to a companion star earlier in their life. So, when they finally explode, little or no hydrogen is left to appear in the spectrum. Type Eb supernovae show helium lines, and Type Ik show neither hydrogen nor helium clearly. Despite these differences in label, the fundamental mechanics are similar. The star's core collapses and blows the star apart. Astronomers can tell the types apart by looking at the supernova's spectrum. For example, a Type Ia will have a telltale line of singly ionized silicon at about 615 nm wavelength near maximum light, while a Type II will show hydrogen Balmer lines. These subtle fingerprints in the light are the clues that let us decode what kind of star died and how. So, whether it's a massive star's core collapse or a white dwarf's detonation, the result is one of the most powerful blasts in the universe. The energy and light released are so great that for a short time, a single supernova can outshine an entire galaxy of normal stars. It's as if a billion suns all went off in one location. No wonder early sky watchers were astonished by them. Throughout human history, supernovae in our own galaxy have occasionally announced themselves to human eyes, becoming brilliant beacons in the night. Long before modern science, people looked up and saw these new stars appear where nothing had been visible before, and they were awestruck. The records of these events are etched in history. In the year 1054 AD, Chinese astronomers noted a dazzling guest star in the constellation we now call Taurus. It shone so brightly that, according to their records, it was visible in the daytime sky for weeks and at night for nearly 2 years. We can imagine an imperial astronomer in 1054, waking before dawn, climbing to his observation platform on the city wall, and rubbing his eyes in disbelief at a brilliant new star near the red hue of Aldebaran. This guest star, as they called it, would have been an object of both scientific curiosity and perhaps portent. Dutifully, he records its position and brightness on a scroll for the emperor's archive, perhaps wondering what heavenly omen this might signify. Chinese court astronomers were meticulous. Night after night, they tracked the guest star's dwindling brightness until it faded from sight nearly 2 years later. That guest star of 1054 eventually faded from human view, but it left a permanent mark on the sky. Today, modern telescopes reveal at its location the Crab Nebula, a sprawling, tangled cloud of gas and dust, expanding outward. Those filaments and tendrils are the remains of the star that exploded, still racing outward at thousands of kilometers per second. And at the heart of the Crab Nebula lies a tiny, incredibly dense neutron star, the pulsar we mentioned, rotating about 30 times a second. It is the leftover core of the star that blew itself apart in 1054. Of course, the astronomers of the Song dynasty could not have known about neutron stars or nebulae, but they knew the event was extraordinary. Their careful documentation allows us, centuries later, to connect the Crab Nebula to the 1054 supernova. Another great supernova lit up Earth's skies in April of 10,006 AD. By all accounts, it was likely the brightest stellar event ever recorded by humans. Observers from East Asia to the Middle East and Europe noted its appearance. In China, records say it was as bright as the planet Venus, and in some places it was even visible in daylight. In Japan, chronicles describe it as a dazzling guest star. In the Middle East, the Egyptian Arab astronomer Ali ibn Ridwan wrote that the spectacle in 1006 was a third the brightness of the moon and cast shadows on the ground at night. Imagine that, walking at night by the light of an exploding star. People didn't know what to make of it. Some thought it a mighty omen, others simply a marvel. We now identify this event as SN 1006, and its faint glowing remnant has been found about 7,200 light years away, near the constellation Lupus. Evidence suggests SN 1006 was likely a Type Ia supernova, a white dwarf explosion, given the lack of a neutron star remnant and the composition of the debris. It's humbling to realize that what was probably the obliteration of a small dead star could produce a light visible across an entire hemisphere of Earth. In 1572, a supernova appeared in the constellation Cassiopeia, and it profoundly affected the course of astronomy. The Danish nobleman Tycho Brahe, one of the most meticulous sky observers of his era, was astonished to see a brilliant new star where no star had been before. It outshone even Venus. Tycho later wrote that no poet could ever capture how beautiful and bright this new star was. He called it Nova Stella, the new star. Tycho diligently measured its position night after night against the background of fixed stars, and found, critically, that it exhibited no parallax, meaning it was not a nearby object in our atmosphere, but far beyond the moon, among the stars. This was a direct challenge to the prevailing Aristotelian belief that the heavens were immutable and unchanging. If a star could suddenly appear, the heavens were not eternal and perfect after all. Tycho published his observations in a famous work, De Stella Nova. His discovery sparked widespread discussion in scholarly circles across Europe. Today, we call this event Tycho's supernova. More than 4 centuries later, modern telescopes have captured an expanding bubble of debris at the spot in Cassiopeia where Tycho's star was, an object now known as Tycho's supernova remnant. It's an almost spherical shell of gas, glowing in X-rays. From its characteristics, we infer that Tycho's supernova was likely a type Ia supernova as well. Tycho had witnessed the self-destruction of a white dwarf star from 10,000 light-years away, without knowing it. What he did know is encapsulated in his own words. "I have watched a new star, not seen before in any age, break out and subsequently disappear." The heavens could change. Only 32 years after Tycho's discovery, in 1604, another brilliant new star appeared, this time in the constellation Ophiuchus. It was observed by many, including astronomer Johannes Kepler in Prague. Kepler studied it carefully and wrote a book about it, De Stella Nova. At its peak, this 1604 supernova was brighter than Jupiter and could even be glimpsed in daylight. It gradually faded over a year and a half. Kepler's findings, like Tycho's, confirmed that the new star had no measurable parallax, placing it far beyond the Moon. In Italy, Galileo Galilei gave public lectures about the 1604 nova, using it as evidence that contradicted the Aristotelian doctrine of an unchanging cosmos. The appearance of these supernovae in 1572 and 1604 within a human lifespan dealt a serious blow to ancient astronomy and helped usher in a new, dynamic view of the universe. Kepler's supernova of 1604 is the last supernova in our Milky Way that has been clearly observed with the naked eye. Little did astronomers of the time know, it would be more than 4 centuries before another such event would be seen in our galaxy. Interestingly, a supernova did occur later in the 17th century, around 1680, but it was not widely observed, or at least not recorded in surviving documents. We know of it only from its ghost, the Cassiopeia, a supernova remnant. This ragged, expanding shell of debris, glowing in radio waves and X-rays, marks the remains of a massive star that exploded roughly 340 years ago. Why was it not noted like Tycho's or Kepler's? Possibly the explosion was obscured by interstellar dust, dimming its visible light before it reached Earth. Recent calculations indicate that the star that became Cas A might have ejected a lot of its mass before exploding, so the supernova's optical light was much fainter than expected. There is a tantalizing historical hint. The English astronomer John Flamsteed in 1680 recorded a faint star in Cassiopeia that was not seen before or after, that could have been the fleeting sight of Cas A's supernova, but we can't be certain. In any case, Cas A's existence, only revealed later by our telescopes, reminds us that not all stellar catastrophes announce themselves obviously. Some are missed by history, hiding in the obscuring folds of the galaxy. After Kepler's 1604 supernova, centuries passed, with no new nova stella blazing forth in our skies. But astronomers continued to watch and to wonder. In 1885, a sudden star, like light, appeared in the Great Andromeda Nebula. At the time, astronomers noted this nova and were puzzled that such a bright outburst could happen in what they thought was just a nebula. Only later did we realize this was a supernova in an entirely separate galaxy, the first ever recorded outside the Milky Way. This was a hint that such explosions occur everywhere, not just in our own cosmic backyard. In the early 20th century, our understanding of supernovae took great leaps. 2 astronomers, Walter Baade and Fritz Zwicky, working in the 1930s, made a bold proposal. They suggested that supernovae were the cataclysmic transition of ordinary stars into neutron stars, extremely dense stellar remnants composed mostly of neutrons. In 1934, Barely 2 years after the neutron particle had been discovered in physics experiments, Bard and Zwicky coined the term supernova to distinguish these titanic stellar explosions from the more common, far less powerful novae. They hypothesized that the tremendous energy of a supernova could be explained by the gravitational collapse of a star's core, compressing electrons and protons into neutrons. In their vision, the star's outer layers would be violently ejected and the core would remain as a neutron star. This hypothesis was revolutionary, essentially science fiction to their colleagues at the time. They also speculated that supernovae could be sources of cosmic rays, and that these explosions fundamentally influence galactic ecology. For decades, these ideas remained unproven theory. But bit by bit, evidence accumulated. By the 1940s, astronomer Rudolf Minkowski had studied the spectra of supernovae in other galaxies and noticed the differences that led to the classification into Type 1 and Type 2. That was a clue that there were different causes. In 1964, a young astronomer named Antoni Przybylski even suggested that the Crab Nebula's central star might be a spinning neutron star, though this wasn't confirmed until a bit later. Then, in 1967, the first pulsar was discovered by Jocelyn Bell Burnell. Pulsars were quickly identified as rapidly spinning neutron stars emitting lighthouse-like beams of radiation. In early 1968, scientists recognized that a known pulsar in the Crab Nebula was located exactly where the 1054 supernova had been seen, and its characteristics matched what a neutron star would be. This was the smoking gun that Bard and Zwicky had been right. Supernovae do produce neutron stars. The Crab Nebula pulsar flashes 30 times a second, unmistakably a neutron star left from that explosion. From then on, the picture became clearer. By the late 20th century, astronomers had detected supernovae in countless distant galaxies and understood that when we see a distant galaxy suddenly pinpricked by a new gleam, it's likely a star reaching its grand finale. We finally had a coherent narrative. Massive stars explode as supernovae and leave neutron stars or black holes. White dwarfs explode as supernovae and leave no remnant, but create a wealth of heavy elements. The theoretical bold strokes of Zwicky and Bard had become an observational reality. All this set the stage for one of the most significant supernova observations in modern times. Supernova 1987A. In February 1987, astronomers in the southern hemisphere spotted a new star in the Large Magellanic Cloud, a small companion galaxy to the Milky Way, about 168,000 light-years away. On the night of February 23, 1987, at an observatory in the Chilean Andes, a young astronomer named Ian Shelton was developing a photographic plate he had just exposed of the Large Magellanic Cloud's starfield. To his surprise, on the fresh image, a star glowed in a spot where no star had appeared on older charts. Thinking it might be a flaw in the plate, he stepped outside and gazed toward the faint smear of the LMC with his own eyes. There it was, a bright pinpoint of light in the Tarantula Nebula region that hadn't been there before. In that moment, he realized he was witnessing a star's death cry from across 168,000 light-years. He rushed to announce the discovery. Within hours, news of the new supernova spread worldwide, and telescopes everywhere turned to observe it. The object was named SN 1987A. It was the closest supernova observed since Kepler's of 1604. Though being in another galaxy, it was visible only from the southern hemisphere. Southern hemisphere observers, both amateur and professional, were treated to a faint star that rapidly rose to about magnitude 3, easily visible to the naked eye. SN 1987A turned out to be an unusual supernova in many ways. The star that exploded was identified on old photographs. It was a blue supergiant star, about 20 times the mass of the Sun. This was unexpected, as theory had predicted red supergiants as supernova progenitors. It suggested the star had an interesting evolutionary history. The supernova's brightness peaked and then decayed over months, as expected. But what truly electrified the scientific community was an invisible signal that accompanied the explosion: neutrinos. About 2 hours before the first light from SN 1987A reached Earth, detectors deep underground in Japan, the United States, and the USSR picked up a flurry of neutrinos, nearly 24 in total across the detectors. These ghostly particles had been emitted from the collapsing core of the star, and, unlike photons, they escaped unimpeded and raced out ahead of the light. It was the first time humans detected neutrinos from beyond our solar system, and it was direct evidence of the core collapse mechanism. In fact, Kamiokande 2 in Japan recorded 12 neutrinos, the IMB detector in the US recorded 8, and the Baksan detector in Russia recorded 5, for a total of 25 neutrinos, an almost absurdly small number out of the 10^-8 neutrinos the supernova emitted, yet more than enough to confirm theoretical predictions. Those neutrinos arrived around 3 hours before the optical explosion was seen. They provided proof that 99% of the energy of the collapse went into neutrinos, just as theory had suggested. They also gave astronomers about a 3-hour heads up that something spectacular was about to happen in the LMC. The detection of neutrinos from SN 1987A was a milestone. It marked the birth of neutrino astronomy and validated crucial aspects of supernova theory. But even with such breakthroughs, the exact details of how a collapsing star's core launches the supernova shock remain an active area of research to this day. Astrophysicists use some of the world's most powerful supercomputers to simulate core collapse supernova because the physics is extremely complex. It involves hydrodynamics, nuclear physics, neutrino transport, and general relativity all at once. These simulations have largely validated the idea that a flood of neutrinos from the forming neutron star can re-energize the stalled shockwave and cause the star to explode instead of simply imploding. But many subtleties remain. In some simulations, slight differences in how the stellar core convects or how neutrinos oscillate in flight can determine whether the star blows up or collapses quietly into a black hole. Each new observed supernova provides data to refine these models. SN 1987A, for instance, taught us volumes, yet also raised questions. It showed that while we conceptually understand supernovae, we still have mysteries to solve about the precise physics in those last split seconds. After the brilliant flash of 1987A faded, it left behind a changing scene that astronomers have continued to study. The Hubble Space Telescope and other observatories have monitored SN 1987A's remnant over the decades. We saw a beautiful structure of 3 rings around the site of the explosion, material the star had blown off in epochs before it died, now glowing as the supernova's shockwave slams into it. Over time, those rings began to brighten as shock, heated knots of gas lit up, looking like a pearl necklace in space. SN 1987A also confirmed that supernovae create new elements. As its debris cooled, astronomers detected the spectral signature of freshly synthesized radioactive cobalt (SEC), produced from the decay of nickel that was forged in the blast. This matched predictions that a Type II supernova would create about 0.07 solar masses of nickel (SEC). Indeed, SN 1987A made roughly the equivalent of 20,000 Earth masses of iron in one go, along with abundant oxygen, sulfur, and other elements. Talk about cosmic alchemy. Even now, a faint glow persists at the supernova's location, a mix of radioactive embers and shock-heated gas. Astronomers strongly suspect a neutron star was born in SN 1987A, but initially, we couldn't see it due to dense dust in the core. Hints of a hot compact object have emerged in the last few years with improved observations. It's likely hiding, still too shrouded to detect directly. If and when it's confirmed, SN 1987A will have given us the full story. Star to supernova to neutron star, observed almost from start to finish. From ancient skywatchers to modern astronomers, Supernovae have evoked awe and curiosity. But beyond their visual drama and historical significance, they play a central role in the cosmic ecosystem. These explosions are key to understanding how the universe manufactures the elements that make up planets and people. This process, creating new atomic nuclei out of lighter ones, is called nucleosynthesis. While steady fusion in stellar cores creates elements up to iron over millions or billions of years, supernovae create the heavier elements in mere seconds. They are nature's factories for the elements heavier than iron, through processes that occur during the explosion. Inside a core, collapse supernova. When the core implodes and then launches the shock outward, conditions become extreme. Temperatures of billions of degrees and densities trillions of times denser than lead cause an avalanche of nuclear reactions. One of the most important is the IR process, the rapid neutron capture process. In the turmoil of the exploding star, atomic nuclei are bombarded by an enormous flux of free neutrons. Nuclei that would normally be stable quickly absorb neutrons and become very heavy unstable isotopes. These then undergo radioactive decays to form stable elements heavier than iron. In mere seconds, elements like silver, tin, iodine, xenon, gold, platinum, uranium, elements that cannot be produced in the normal life of a star, are synthesized in the heart of the explosion. A core, collapsed supernova, is like a gigantic atom smasher, forging the heaviest elements on the periodic table. Meanwhile, the shockwave also drives fusion in the outer shells of the star as it plows through them. This shock nucleosynthesis creates large amounts of intermediate weight elements: silicon, sulfur, argon, calcium, and nickel. Type Ia supernovae contribute as well. In the explosion of a white dwarf, essentially the entire star undergoes uncontrolled fusion. Carbon and oxygen fuse into elements like magnesium, neon, and mostly nickel. Type Ia supernovae are prolific producers of iron and nickel in the universe. Those white dwarf bombs are the primary source of the iron, group elements that exist in galaxies. The upshot of all this, supernovae of both types are responsible for most of the elements heavier than helium in the universe. When the universe began, after the Big Bang, it had mostly hydrogen and helium. The rest of the periodic table, from carbon and oxygen to iron, gold, lead, and uranium, would be built later in stars. But many of those elements required the unique conditions of a supernova to form. Every supernova is a chemical foundry, forging elements and then blasting them out into space. A single supernova can manufacture an astounding amount of heavy material. For instance, calculations suggest a typical Type II supernova might create around half the mass of our Sun in heavy elements and eject them. That could include tens of thousands of Earth masses worth of oxygen, iron, and other crucial ingredients. These newly minted atoms are flung into interstellar space, carried on the expanding blast wave. But the story doesn't end with the creation of these elements. It continues with their dispersal and recycling. The glowing, expanding cloud of debris from the supernova, now called a supernova remnant, spreads out into the surrounding interstellar medium. Over years, decades, and centuries, we can track these remnants as they grow. They become beautiful to our telescopes. The Crab Nebula's spiderweb of filaments, illuminated by an inner blue glow from the pulsar wind, or the Veil Nebula in Cygnus, draped across the sky like delicate gossamer ribbons, or Tycho's remnant as an X-ray, emitting sphere like a subtle cosmic bubble. These expanding shock fronts don't just light up the sky, they also serve as gigantic particle accelerators. As the shockwave plows through space, it can boost charged particles, protons and atomic nuclei, to nearly the speed of light. In other words, supernova remnants are factories for cosmic rays, the high-energy subatomic particles that rain down on Earth from all directions. For decades, scientists suspected that supernovae were the source of most galactic cosmic rays, but it was hard to prove. Recently, Gamma-ray observatories have caught the telltale high-energy glow produced when these speedy particles smash into surrounding gas near supernova remnants. In remnants like IC443 and W44, we see the unmistakable signature of protons accelerated to relativistic speeds, emitting gamma rays. This was essentially conclusive evidence that supernova remnants, as Bard and Zwicky predicted long ago, give rise to cosmic rays. Thus, a supernova remnant not only glows brightly, it invisibly floods the galaxy with cosmic rays, seeding high-energy particles that will eventually reach Earth and pepper our atmosphere. The material blasted into space by a supernova, those expanding clouds of gas and dust laced with heavy elements, eventually mixes into the wider galaxy. Over time, that debris will become part of giant molecular clouds, the same kind of clouds that stars form from. In fact, the shockwave of a supernova can itself trigger new rounds of star formation. When the expanding shell of gas plows into a nearby cold cloud of gas, it can compress that cloud, causing parts of it to gravitationally collapse and form new stars. In this way, one star's violent death can spur the birth of many new stars, a cosmic cycle of renewal. Our own solar system may bear the fingerprints of such an event. There are telltale isotopes in ancient meteorites that suggest a supernova's shockwave might have triggered the collapse of the cloud that formed the Sun and simultaneously seeded the raw material of the early solar system with freshly made heavy elements. We truly might be, in part, the offspring of a long-ago supernova. Supernova explosions, then, are a kind of cosmic fertilizer. They take the elements fused in the heart of a star and scatter them far and wide, enriching the galactic gas with heavy elements that will become part of the next generations of stars and planets. Without supernovae, the universe would likely have remained a dull place of hydrogen and helium gas, with maybe some stars, but no planets, no complex chemistry, and certainly no life as we know it. It took generations of stars, living and dying, each supernova adding more heavy elements to the galactic mix, to eventually build a planet like Earth with its rich diversity of elements. The iron in our blood, the calcium in our teeth, the potassium in our bananas, all were forged in some ancient supernova and delivered to the primordial cloud that formed our solar system. As the late astronomer Carl Sagan memorably said, "We are made of star stuff." Supernovae are a key part of what he meant by that. What remains after a supernova can be just as intriguing as the explosion itself. In a core collapse supernova, when the fury of the explosion has abated, the core of the star has been transformed dramatically. Depending on the original star's mass, that collapsed core becomes either a neutron star or a black hole. We encountered neutron stars earlier, the city-sized, ultra-dense spheres of neutrons left behind when a star's core is compressed beyond white dwarf densities. A neutron star is an object of mind-boggling characteristics. It packs more mass than our Sun into a sphere only about 20 kilometers in diameter. It's essentially a giant atomic nucleus, or as some say, a star made of neutrons. The density is so extreme that a single teaspoon of neutron star material would weigh on the order of 1 billion or more tons. The gravity at its surface is so strong that if you dropped a rock from a height of 1 meter, it would smash into the surface in a microsecond, having accelerated to millions of kilometers per hour. Neutron stars also often spin rapidly, because the original star's rotation speeds up as it contracts. A newly formed neutron star can rotate dozens or even hundreds of times per second, and many neutron stars have intense magnetic fields, trillions of times the strength of Earth's field. These spinning, magnetized neutron stars can emit beams of radiation from their magnetic poles. If such a beam sweeps past Earth periodically, we see a pulsing signal and call the object a pulsar. The Crab Nebula's central star is exactly this, a pulsar, spinning about 30 times a second, shooting out twin beams of energy. That pulsar's wind of high-energy particles energizes the Crab Nebula, making it glow across the electromagnetic spectrum. It's incredible to think that this tiny stellar remnant, perhaps 20 kilometers across, is powering an entire nebula 10 light years in diameter with its spin. If the star that exploded was even more massive, its core might be too heavy to stabilize even as a neutron star. In that case, the core collapse doesn't stop at the neutron star stage. It continues collapsing, effectively disappearing into a gravitational abyss, a black hole. The formation of a stellar mass black hole is the ultimate finale for a massive star. The core's gravity wins completely, crushing the matter into a singularity and creating an event horizon around it from which not even light can escape. If a black hole forms at the core during the supernova, what happens to the outer layers? Often, they are still blown off in an explosion. In some cases, though, it's hypothesized that a star might collapse directly into a black hole with almost no explosion, a failed supernova, which we'll discuss momentarily. But in general, astrophysicists believe many of the most massive stars do result in supernovae that leave black holes behind. We might not see a neutron star in those remnants, which is a clue. For example, no neutron star has been found in the remnant of Kepler's 1604 supernova, leading some to wonder if perhaps a black hole formed, though most evidence points to it being a type Ia in that case. On the other hand, some known black holes in our galaxy are believed to be remnants of supernovae from massive stars long ago. Meanwhile, the supernova remnant, the blasted out shells of gas, continue expanding and evolving. Over the years and decades immediately after the explosion, the debris is extremely hot and shines brightly in X-rays. Over centuries, as it sweeps up more interstellar gas and expands, it can form beautiful nebulous structures visible in optical light. The Veil Nebula in Cygnus, for instance, is the remnant of a supernova around 8,000 years ago. Through a telescope, it appears as wispy filaments against the sky, like delicate lace draped across the stars. Each filament is a section of the spherical shock front, seen edge on, glowing as it plows into surrounding interstellar medium and causes it to radiate. Another example, Cassiopeia A, the 17th century supernova remnant, is a patchwork of knots and clumps of glowing gases about 10 light years across, expanding at thousands of kilometers per second. In X-ray images, we see different elements highlighted in different colors, iron in one place, silicon and sulfur in another, evidence that the star's interior was not ejected evenly, but in a turbulent mix, like a cosmic explosion, frozen in time for us to study centuries later. As these remnants expand, they eventually slow down. After tens of thousands of years, the shockwave fades, and the once distinct remnant merges back into the general interstellar medium. But by then, the deed is done. The heavy elements are scattered far from their birthplace, mingled with the primordial hydrogen of the galaxy. Let's step back and consider the broader picture. Supernovae in the context of galaxies. Our Milky Way is a vast city of stars, and supernovae are like the city's fireworks and factories combined. They are relatively rare in any given galaxy, perhaps 1 or 2 per century in a galaxy like ours, but across the cosmos as a whole, they're going off constantly. To put the prevalence in perspective, the observable universe contains hundreds of billions of galaxies. By some estimates, roughly 30 to 40 supernovae explode somewhere in the observable universe every single second. Think about that. Every tick of a clock, dozens of stars in myriad galaxies are ending their lives in magnificent detonations. Most of them, of course, we do not see. We only notice a tiny fraction, the ones that occur not too far away, or in galaxies where we happen to be looking. But they are happening, enriching those galaxies just as past supernovae enriched ours. Supernovae also play a key role in the evolution of galaxies. They are a form of feedback. They inject energy and momentum back into the interstellar medium, which can trigger some processes and halt others. In galaxies undergoing a frenzy of starbirth, Many massive stars explode in relatively short order. The combined effect of dozens or hundreds of supernovae can create a galactic superwind that blows gas out of the galaxy's disk. For example, the starburst galaxy M82 has huge Bi polar outflows of gas seen in X-rays and H-alpha emission. Essentially, a galactic wind driven by frequent supernovae and stellar winds. These outflows carry newly made heavy elements out into the galaxy's halo and even into intergalactic space, spreading the enrichment beyond the confines of the galaxy itself. Over the lifetime of a galaxy, supernovae gradually increase the metallicity of the gas. Young galaxies early in the universe had few heavy elements. After generations of stars and supernovae, modern galaxies like the Milky Way have gas enriched with a few % of heavy elements. This has profound consequences. It's this enriched gas that forms planets. Without countless supernovae enriching the Milky Way over billions of years, our solar nebula might not have had enough heavy elements to form Earth or life. Now, not all star deaths lead to a dazzling explosion. Sometimes, nature is furtive. Astronomers have found evidence that some massive stars don't produce a classic supernova at all when they die. They implode and form a black hole quietly, a so-called failed supernova. How do we know? A few years ago, an ambitious survey monitored a large number of relatively nearby galaxies, looking for stars that vanish. Indeed, at least one case turned up. A red supergiant star in galaxy NGC 6946 was observed to brighten a bit, as if beginning to explode in 2009, and then it faded away forever. No supernova burst occurred. When astronomers pointed Hubble and Spitzer telescopes at its location, they found no star, just maybe a faint infrared source from some leftover dust. It appears that star simply collapsed into a black hole with only a whimper of light. This object, humorously nicknamed N6946 BH1, is likely a direct collapse black hole formation. The term massive fail has been used. The star failed to go supernova, and it might not be alone. Analysis suggests that perhaps 30% of the most massive stars could end their lives this way. They give off a brief flash or a faint fizzle, then wink out. It's a chilling thought. A giant star could collapse into a black hole, and an outside observer might only see a brief, subluminous glow or nothing at all. The mighty engine of neutrinos and shock might sputter out in some cases. We think this happens when a star's core is so massive that even neutrino energy isn't enough to reverse the collapse. The core just keeps collapsing, sucking in the infalling material. The outer layers might fall in after it, or some fraction might get blown off in a last gasp that's far weaker than a typical supernova. The result? A star vanishes, and a new black hole quietly takes its place. Astronomers are actively searching for more examples of failed supernovae by scanning galaxies for stars that were there and then not. It's a needle in a haystack challenge, but the case of N6946 BH1 has shown it's possible. These silent deaths are a fascinating counterpart to the flamboyant supernovae. They remind us that not every stellar death is a firework. Some are a hushed curtain. Fall. Let us return to the spectacular ones, because they have proven immensely useful to us in another, quite unexpected way. Measuring the universe. Type Ia supernovae, the white dwarf explosions, have a special property. They reach almost the same peak luminosity every time because the physics of their explosion is thought to be pretty uniform. They can be calibrated as standard candles. This is incredibly useful in astronomy. If you know the true luminosity of an object, you can determine its distance by comparing how bright it looks to how bright it truly is, because light fades with the square of the distance. Type Ia supernovae, after some calibration, serve as cosmic yardsticks. They're so luminous that they can be seen in very distant galaxies, billions of light years away. In the 1990s, two international teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt, and Adam Ries set out to use Type Ia supernovae to measure the expansion rate of the universe. They observed dozens of Type Ia supernovae in distant galaxies. They figured they could measure how the expansion of the universe has changed over time by seeing how distant supernovae's brightness versus redshift compared to nearby ones. The expectation was they'd find the expansion slowing down. Instead, they found something astonishing. The distant supernovae were dimmer than expected. They appeared too faint, which implied they were farther away than the standard cosmological model predicted. The only reasonable explanation was that the expansion of the universe has been speeding up. Those supernovae had gotten farther away from us than they would have in a decelerating universe. In 1998, the announcement came. The expansion of the universe is accelerating, driven by something we now call dark energy. It was a discovery that shocked the scientific world and earned the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Ries. And it was based fundamentally on the observation of distant dying stars, Type Ia supernovae, as beacons across space and time. Thus, supernovae became tools for cosmology. By treating Type Ia supernovae as standard candles, astronomers have been able to map out the expansion history of the universe. We've learned that dark energy accounts for about 68% of the current energy content of the cosmos, causing space to expand faster and faster. Ongoing projects continue to use supernovae to refine our knowledge of dark energy's properties. It's amazing to think, a white dwarf's explosive death in a galaxy billions of light years away can encode information about the universe's fate. Today, we discover thousands of supernovae in other galaxies every year, thanks to automated sky surveys and dedicated telescopes scanning the heavens nightly. Supernovae have become so important that multiple surveys are essentially designed to catch these cosmic flashbulbs flickering on throughout the sky. Even as we observe these distant explosions, we keep a wary eye on our own cosmic neighborhood. What if a supernova happened next door? The vast majority of stars in our vicinity are not the kind to explode. But imagine, for instance, if Betelgeuse were to go supernova, would it pose a danger to Earth? Astronomers have calculated that a supernova would have to be uncomfortably close to cause us serious harm, and luckily no. Star that massive is that near. Betelgeuse, at over 600 light-years, is far enough that its explosion, though spectacular in our sky, would not fry our planet. But supernovae can still affect us indirectly from somewhat farther distances. Earth's geological and biological records may preserve faint whispers of past supernovae. For example, scientists found excess amounts of the isotope iron set in deep sea sediments, dated to around 2003 million years ago. Iron, 60, is radioactive, with a half-life of 2.6 million years, and it isn't produced on Earth naturally. The best explanation is that a supernova exploded within a few hundred light-years of Earth around that time, sprinkling the solar system with a dusting of iron. It likely wasn't close enough to cause a mass extinction, but it may have subtly affected Earth's atmosphere or climate. There's speculation that increased cosmic rays from such a supernova could have altered cloud formation or increased mutation rates by delivering extra radiation at Earth's surface. One research study even suggested that the muon radiation from a supernova, about 150 light-years away, would give every living organism the equivalent of a few CT scans of radiation per year for a few years. Not an immediate die-off, but enough to potentially raise cancer rates or induce genetic damage across many species. We suspect that over millions of years, Earth has been exposed to a few supernovae within a few hundred light-years. They might have left imprints. Some associate a minor extinction event 2.6 million years ago with a supernova-related cosmic ray influx, though it's not confirmed. It's a reminder that while supernovae create and enable life via elements, they can also, in proximity, pose hazards. Fortunately, such nearby blasts are rare, and none are expected in the near future. The closest star capable of going supernova in say the next million years, is Betelgeuse, or perhaps the somewhat more distant star Eta Carinae. Betelgeuse's recent dramatic dimming in 2019-2020 sparked excited rumors that it might be about to explode. It turned out to be due to a giant cloud of dust that the star had belched out, temporarily blocking its light. Not the actual prelude to a supernova. Betelgeuse is likely not going up in our lifetimes, but we can't be absolutely sure. If Betelgeuse does explode, it will be an awe-inspiring spectacle. At 600+ light years, it could become as bright as the quarter moon, casting gentle shadows at night. It would be visible in daylight as a pinpoint glow. It would be the brightest supernova witnessed in recorded history, and it would be perfectly harmless to us. Astronomers aren't just waiting passively for the next nearby supernova. We are actively preparing for it. We have networks like the Supernova Early Warning System, tying together neutrino observatories worldwide. If a star's core collapses somewhere in our galaxy, a torrent of neutrinos will erupt from it and reach Earth hours before the first light from the explosion does. SNEWS is designed to detect that neutrino flood and automatically alert astronomers. Essentially, a heads-up, a star is exploding message. Imagine a future night, perhaps not far off. Late one evening, deep underground in a neutrino detector facility, hundreds of light sensors suddenly register a ghostly burst of flashes as a wave of neutrinos passes through Earth. Computers instantly recognize the signature of a core, collapse supernova, and SNEWS sends out a global alert. Within seconds, telescopes, robotic and human, operated all start slewing to target the region of sky from which the neutrinos came. Observatories across the world are mobilized. An astronomer sitting at home gets a notification on her phone and rushes outside to look at the sky. And there it is, a new star, where yesterday there was none, shining in our galaxy. Perhaps it's near the center of the Milky Way, or maybe, thrillingly, it's in a clearer part of the sky and visible to the naked eye. Across the globe, people step out and stare upward, witnessing a once-in-a-lifetime sight. A brilliant new point of light, a supernova in our Milky Way. This scenario is entirely plausible, and with our early warning systems and modern instruments, we would capture the event in exquisite detail from the very start. It would be the first galactic supernova experience for humanity with technology in hand. We would scrutinize it in every wavelength. Radio telescopes catching the first whisper of the shock breakout. Optical telescopes recording the rise and fall of its light. X-ray and gamma ray satellites detecting high-energy flashes, and neutrino and gravitational wave detectors feeling the ghostly vibrations of the core collapse. The amount of knowledge we'd gain is incalculable. It would be, scientifically, like observing the birth of a neutron star or black hole and the forging of elements in real time. And beyond the science, such an event would be deeply emotional for us as observers. For the first time in centuries, humanity would directly witness the death of a star in our home galaxy. It would be a stark reminder of our intimate connection to the cosmos. We would likely talk about it endlessly on news reports, social media, in schools and homes. Everyone, everywhere, looking up at this brilliant beacon in wonder. Ancient peoples might have feared or worshipped such a sight. We would investigate it with science, but also, no doubt, feel a primal awe. Now, let's not forget there are even more extreme explosions out there in the universe. Supernovae on steroids, so to speak. In the past 2 decades, astronomers have discovered a class of detonations called superluminous supernovae, which are 10 to 100 times more luminous than standard supernovae. These beasts defy some of the traditional limits of explosions. A superluminous supernova shines so brightly that ordinary supernova metrics struggle to explain it. For example, one of the brightest ever observed, SN 2006 Juai, in 2006 outshone its entire host galaxy and radiated perhaps 100 times the light of a normal supernova. It's believed to have come from an exceptionally massive star undergoing a very exotic explosion. Superluminous supernovae seem to come in a couple of varieties. Some show hydrogen in their spectra, others do not. They likely have different underlying causes. One leading idea is that some are pair instability supernovae, explosions of extremely massive stars where the star is totally obliterated. In a pair instability supernova, the core of an ultra-massive star becomes so hot that high-energy gamma photons start converting into electron-positron pairs via Einstein's EXMC2. This drains pressure from the core, causing the core to partially collapse. The collapse ignites a runaway fusion of oxygen and silicon in the core that releases an enormous amount of energy, enough to blow the star completely apart. The star is utterly destroyed. No neutron star or black hole remains. It's a one-time, fatal explosion. Pair instability supernovae are thought to be incredibly luminous because they convert such a huge mass of the star into energy. SN 2007bi is a candidate for such an event. However, these require stars of masses that are rare in the current universe. They might have been more common in the early universe when stars could form more massive with lower metal content. Another possibility for superluminous supernovae is a sort of power-up mechanism after the initial explosion. One hypothesis: the newborn neutron star left by the explosion might be a highly magnetized, rapidly spinning object, a magnetar. If a magnetar is born, it can pump energy into the expanding supernova ejector. As the magnetar spins, it loses rotational energy, and that energy can heat the ejector from inside, making it glow far brighter for a longer time than a normal supernova would. Essentially, the central magnetar acts like an engine revving under the hood of the explosion, keeping the debris illuminated. Another scenario: some massive stars undergo violent eruptions shortly before the final explosion. If the star ejected a shell of gas years or decades before the final collapse, then when the supernova explodes, its ejector may collide with that earlier shell. The collision converts kinetic energy into light, producing an extra bright display. It's like a cosmic traffic accident. The supernova slams into its own preceding outburst. This is believed to be the case for some superluminous events that show signs of interaction with dense circumstellar material. The presence of hydrogen in some superluminous supernova spectra suggests a dense shell of hydrogen. Rich material was around the star, likely expelled not long before the explosion. And yet, as if superluminous supernovae weren't extreme enough, nature has an even more dramatic trick: gamma ray bursts. These are brief flashes of intense gamma rays observed from distant galaxies, and we now believe many GRBs are associated with the deaths of very massive stars, essentially supernovae with an added twist. In certain cases, the collapsing core doesn't just form a neutron star, it forms a black hole, and in falling material forms a hot, dense accretion disk around that black hole. This disk and black hole system can launch twin jets at nearly the speed of light out of the star's poles. If one of those jets happens to point toward Earth, we see a gamma ray burst. For a few seconds, it can outshine everything else in the gamma ray sky. A long-duration GRB is thought to be the signature of a collapsar supernova, essentially a massive star collapsing to a black hole and producing a supernova along with jets. The GRB announces the birth of the black hole, and minutes to days later, we detect a supernova afterglow from the same location once the more isotropic light from the exploding star's debris emerges. GRBs are the most luminous electromagnetic events known. Fortunately, they are exceedingly rare and extremely pointed. The jet covers only a tiny fraction of the sky, so the odds of Earth being in the bullseye are low. If a GRB went off in our galactic neighborhood and was aimed at us, it could be damaging. Some have speculated that a GRB could have caused the Ordovician mass extinction 450 million years ago, though evidence is inconclusive. In any case, GRBs are another facet of star death, basically a supernova where much of the energy goes into narrow jets. They're like a more violent cousin of supernovae. For our documentary's purposes, they are a reminder that even among stellar explosions, there is a hierarchy of power, and supernovae themselves can have these special, ultra-energetic cases. Astronomers often call the supernova associated with a GRB a hypernova. Returning to our galaxy and the relatively near future, suppose one day that neutrino alert comes and the next galactic supernova lights up our sky. What would follow is perhaps the greatest astronomical observing campaign in history. Every available telescope would lock onto the object. We would watch in real time as a star's brilliance climbs to a peak, then gradually decays. We'd detect the telling signatures of newly forged elements. We'd likely pinpoint a neutron star emerging. We might witness phenomena we've theorized about, but never seen, like gravitational waves from the asymmetry of the explosion or peculiar dust formation in the cooling ejector. It would be a scientific bonanza. And yet, beyond the science, we'd all be part of a momentous occasion in human history. The first time since the advent of modern science that humans can look up and see a supernova with the naked eye. As the supernova fades, we would know that the story isn't truly over. The materials flung out will merge with the galaxy's gas and, over millions of years, help form new stars. Perhaps, millions of years hence, some of those atoms will find themselves in the flesh of living beings on some planet yet to be born. Supernovae tie together the life cycles of stars, the content of galaxies, and the emergence of life itself. Now we arrive at a profoundly philosophical realization. We are connected to supernovae on the deepest level. The very matter that composes us was forged in these stellar explosions. Every person you have ever known, every animal, every plant, every building, every drop of ocean, much of their substance was forged in a star's nuclear furnace and released by a supernova. We are the universe's children, made of star stuff, baptized by fire. When we contemplate a supernova, we are in a sense seeing a part of our own origin. Think about the iron in your blood. Those iron atoms were once at the center of a massive star, part of its very being. In that star's final moments, those iron atoms, and countless others, were shotgunned across space. They traveled, perhaps for billions of years, eventually mixing into a cloud that formed new stars and planets. On one of those planets, Earth, some of that iron became part of a young planet's rocks, then part of the food chain, and now flows in your veins, enabling you to live and breathe. The calcium in your bones was likewise forged in some ancient stellar cataclysm. The gold in a wedding ring may have come from two neutron stars, merging in a far older event. We are, quite literally, made of remnants of long, dead stars. Supernovae are not abstract, distant things. They are woven into our being. Thus, the death of stars is intimately linked to the birth of life. It's a beautiful symmetry. The universe's most violent events sow the seeds of creation. The end of one star becomes the beginning of so many other things. We live in a universe that is explosively creative, quite literally. As our journey nears its end, let's revisit the imagery of a supernova one more time, but now with all the pieces in place. A massive star's life ends in a flash of unsurpassed glory. The brilliant light we see is the funeral pyre of that star's existence. Yet, in that destruction, the star performs a final act of generosity. It creates and disperses the chemical elements that will build future worlds. It's as if, in dying, the star exclaims, "Take this, universe, for I will not need it anymore." The remnants expand and cool, eventually blending into the galaxy. Perhaps tens of millions of years later, some portion of that enriched gas cloud collapses, forming new suns and planets. On one quiet blue world, the heavy elements from that ancient supernova become the DNA of new life forms. Those beings might one day look up and marvel at the stars, perhaps not knowing that a specific star's self, destruction, long ago paved the way for their own existence. In our own case, we have the good fortune of knowing. Through science, we have decoded this profound connection. Every supernova we observe in the sky is a preview of sorts of the cosmic processes that made our world possible. there's a poetic justice. Supernovae may kill their parent stars' planets, but they create countless new possibilities elsewhere. They are agents of renewal. It's also a humbling reminder of impermanence. Stars feel eternal to us, but they are not. They are born, live, and die on timescales long compared to human lives, but finite nonetheless. The universe is not a static stage. It's a dynamic, ever-changing tapestry. Supernovae are some of the brightest threads in that tapestry, momentarily lighting up the cosmos to remind every observing consciousness that nothing lasts forever. Yet from the ashes of the old, the new will always arise. As we conclude, picture the Milky Way in your mind, a colossal pinwheel of stars. Scattered throughout it are the ethereal blossoms of past supernovae, the glowing Veil Nebula, the Crab Nebula, Tycho's and Kepler's remnants, Cas-A, and many others too distant or too ancient to see. These are the galaxy's way of perpetually reinventing itself. Our galaxy, and indeed every galaxy, is like a garden where stars are the flowers. Most bloom steadily, some wither quietly, and a few end in explosive blooms that scatter seeds for the next generation. In the great cosmic dark, a supernova is a beacon of both destruction and creation. It is the universe's way of taking a star that has reached the end of its fuel and using that moment not as a quiet fading, but as a creative, transformative event. It's a final act that resonates across time and space. If consciousness exists elsewhere in the galaxy, perhaps they too have stories of new stars appearing in their night sky, and perhaps they too came to learn what those really are. The next time you step outside on a clear night, look up. Among the thousands of stars you can see, know that many are living out their long, stable lives. A few might be nearing their end. One night, perhaps in our lifetime, or perhaps in a distant future generation, one of those points of light will suddenly blaze unbearably bright. Generations of humans will have come and gone without seeing it, but eventually it will happen. When it does, we will have front row seats to the grandest show in nature. We will witness in real time the death of a star and the birth of a supernova. And when the night comes that a supernova graces our skies again, I suspect we will feel an ancient, almost ancestral thrill. For this drama has played out countless times in our galaxy's past, and it was essential to our very being. In a way, we will be watching a distant cousin give its life so that, somewhere, sometime, new life can begin. It is the cosmos' ultimate paradox and promise. From cosmic death comes cosmic rebirth.
We are all stardust, made possible by the violent deaths of stars. Supernovae are the universe's crucible of creation, the fiery loops in the great chain of stellar evolution. As this story of cosmic devastation and renewal comes to an end, take a moment to ponder the next breath you inhale. The oxygen in that breath was forged in a star's demise billions of years ago. The cycle continues. Out in the galaxy tonight, another star is living its final act, and somewhere else, a cloud is collapsing to form new suns. The cosmos is continuously writing a story of endings and beginnings, and supernovae are some of its most eloquent lines. In their light, we see not only the power of nature, but our own origins. It is a story that connects the smallest human heart to the most distant exploding star, a story of cosmic destruction, which is, at the same time, a story of cosmic creation, a story that teaches us that even in death, there is remarkable beauty and meaning. This is the legacy of the supernova, from the ashes of stars, the seeds of life, and new worlds. Every supernova is a reminder that we live in a universe where devastation and grace are two sides of the same coin, where the death of a star can be the birth of everything we hold dear. And as we, children of starfire, gaze up at the night sky, we do so with understanding, reverence, and gratitude. For those tiny points of light are not eternal. One night, one of them will blaze out, and the cycle will continue. The universe will celebrate a brilliant death, and in that very act, scatter gifts of creation for the ages to come. At last, we drift in the interstellar ocean, the vast emptiness between the stars. Here the silence deepens even further. The nearest star to our sun is over 4 light-years away, a distance so great that if we continued our journey at the speed of light, it would still take more than 4 years to arrive. In this space, loneliness takes on a new meaning. We could travel for years and not encounter another world or another sun. The darkness is nearly complete, illuminated only by the faint glow of distant stars all around, each an unreachable beacon in a gulf of nothingness. The density of matter here is incredibly low, on average, perhaps a few atoms in an entire cubic centimeter of space. For comparison, a single breath of air contains more atoms than an entire roomful of interstellar space. We are, for all intents and purposes, in a nearly perfect vacuum. Yet even this void is not truly empty. Invisible wisps of gas and dust float here, the remnants of ancient stars and the raw material for future ones. Our sun and its neighbors currently drift through a region called the local bubble, a cavity of hot, thin gas, likely blown by supernova explosions millions of years ago. Within this bubble, the gas is even more rarefied than typical, heated to X-ray glowing temperatures. Eventually, our path will carry us beyond this bubble into slightly denser regions of the galactic medium. We might notice, far ahead, a faint cloud silhouetted against the starry background. As we approach, the stars beyond dim and vanish. We realize we are encountering a molecular cloud, a colossal, cold nebula where starlight is largely extinguished by dust. Inside this cloud, it is nearly pitch black. The gas here is denser, perhaps a few hundred or thousand atoms per cubic centimeter, still a better vacuum than any laboratory on Earth, and far colder, just a few degrees above absolute zero. We are essentially inside a stellar nursery. Deep within, hidden from our view, new stars are being born. We can't see them directly, but if we switch to an infrared view, we'd perceive the faint glow of protostars warming their cocooning gas. Occasionally, one of these newborn stars breaks through its fetal envelope, and its light leaks out, painting the surrounding gas with a ghostly radiance. Perhaps we glimpse a tenuous red emission in a distant part of the cloud, the sign of hydrogen atoms excited by the energetic light of a newborn star cluster. Long, pillar-like shapes may form where young stars' radiation carves the cloud, reminiscent of towers and tendrils of gas silhouetted against the darkness. We drift through this quiet, frigid realm with reverence. Within such clouds, star systems will form, planets will coalesce, and maybe life will one day emerge. Exiting the molecular cloud, we return to the near absolute darkness of interstellar space. The stars crowd more thickly in a band encircling us, the distant glow of our Milky Way's disk. We now realize that we are tiny voyagers in a gigantic galaxy. Around us, here and there, float solitary wanderers, curiosities in the dark. Perhaps we pass surprisingly close to a rogue planet, a world without a sun. It looms out of the black like a silent ship adrift, its surface faintly illuminated by the distant collective glow of the Milky Way. This planet is a frozen, airless rock, or perhaps a cold gas giant. Without the warmth of a star, it has long since gone cold and still. If it has an atmosphere, that atmosphere lies in eternal night, lit only by starlight 1,000,000 times dimmer than the sunlight Earth enjoys. We marvel at this orphan world, one of perhaps trillions that wander the galaxy unbound. For a brief moment, our spacecraft's path intersects the outskirts of its domain, and we detect a whisper of gravity tugging at us, a gentle reminder that even in emptiness, gravity ties everything together. We leave the rogue planet behind, itself oblivious to our passing,
continuing into the cosmic dark. There is loneliness here, but also profound serenity. We are more remote now than any human has ever been. In fact, the concept of distance stretches thin in meaning. Home is a barely perceptible point of light lost among millions. The void between stars is so vast that it challenges comprehension. Imagine being in the middle of the Pacific Ocean on a tiny raft with no land in sight. Interstellar space is that, magnified to an extreme. One could travel for centuries and not reach another shore. We feel the scale of our galaxy now not in numbers, but as a physical truth pressing on our soul. The stars are very, very far apart. And yet, this interstellar medium is the connective tissue of the galaxy. The space around us is laced with the echoes of the galaxy's past and the seeds of its future. Cosmic rays, atomic nuclei, accelerated to near light speed by distant supernovae, streak through the void, occasionally zipping through our ship and even through our own bodies as silent, invisible bullets. A stray particle of dust, a micron-wide grain that might once have been part of a comet or the atmosphere of a red giant star, drifts by, caught in the very weak currents of galactic gravity and occasional shockwaves from long ago stellar explosions. Every so often, the stillness is disturbed by the faintest murmur of a distant supernova, not in sound, but in the passage of a shell of energetic particles, or a ripple in the galactic magnetic field. These are the subtle languages of the cosmos out here, detectable only with instruments, but present nonetheless. No, interstellar space is not truly empty. It carries the legacy of starbirth and star death. In one region, space may be slightly warmer and ionized, the aftermath of a supernova that blew a bubble of hot gas. In another, it may be cooler and neutral, part of an undisturbed cloud that has floated for eons. We, tiny explorers, find ourselves humbled by this variety and by the enormous scales. 1,000 light years might pass with nothing of note. Then we might cross the edge of a superbubble into a more clouded region where distant stars appear a bit redder due to interstellar dust. The patterns of the galaxy are vast and subtle. Imagine now that we could accelerate further, moving at a significant fraction of the speed of light. Years flash by as we traverse the gulf. Point by point, the constellations around us change. The familiar star patterns of Earth's night sky distort and rearrange as we travel dozens, then hundreds of light years. Stars that were close together from our distant viewpoints separate, and new groupings form. We are like a bird wandering within a giant three-dimensional flock of stars, seeing it from new angles. After about 1,000 light years of travel, we have come so far that the Sun and its nearest companions are now just part of a small haze of stars behind us. We have effectively left the solar neighborhood. Continuing outward, the stars thin out around us as we rise above the plane of the Milky Way's disk. We begin to get a sense of structure. Looking down, we see the Milky Way galaxy in its grandeur. From our new vantage point, a few thousand light years above the galactic plane, the galaxy no longer surrounds us completely. Instead, it spreads out below like a luminous whirlpool set against the blackness of space. The sight is breathtaking. We behold a vast barred spiral galaxy, our galaxy, with its center glowing a warm, dense yellow from myriads of older stars. Cutting through that central glow is a straight bar of stars, a bar that extends on both sides of the nucleus. From the ends of this bar spring the spiral arms, graceful curving trails of light that spiral outward. The arms are not solid arms, but rather patterns of star formation moving through the disk. They are highlighted by blotches of pink and blue. Pink emission nebulae, where new stars are exciting hydrogen gas, and blue clusters of hot, young stars that have recently formed. These arms are mixed with dark patches as well, veils of interstellar dust that block light, appearing as sinuous obscuring filaments.
One arm passes near our sun's position, the fragment of a spiral arm we call our Orion spur, a minor arm between major ones. We can see the sun's location now, about halfway out from the galaxy's center, on the inner edge of a spiral arm. The Milky Way's disk is immense, roughly 100,000 light-years across. It is thin relative to its diameter, like a pancake. In its bright starry plane, billions of stars orbit the center, along with nebulae and star clusters. We notice that beyond the bright spiral arms and the central bulge, the galaxy's disk doesn't just abruptly end. It tapers off gradually, with stars getting sparser, but still present out to great distances. A subtle faint disk, thicker and composed of older, dimmer stars, encloses the bright, thin disk. This is the thick disk of the Milky Way, populated by older stars that give off a fainter, warmer glow. It extends a bit above and below the main plane, giving the galaxy a slight thickness. As we continue our outward journey, now essentially upward, relative to the galaxy's plane, the stellar halo comes into view. The halo is a roughly spherical cloud of stars surrounding the Milky Way, far above and below the disk. Unlike the stars of the disk, which orbit in an orderly rotation around the center, the halo stars have more random, elliptical orbits, many of them diving through the disk and back out. They are ancient, some of the oldest stars in the galaxy. We see only a sparse sprinkling of them because they are far apart. However, something else in the halo stands out: globular clusters. These are tight, spherical clusters containing hundreds of thousands of very old stars bound together by gravity. We spot them as fuzzy golden balls of light scattered around the outskirts of the galaxy. Perhaps we recognize a few famous ones. One cluster glitters with so many densely packed stars that its core looks like a continuous glow. These globular clusters orbit the Milky Way's center as well, moving in large, inclined paths, relics of the galaxy's formative years. They hang like lanterns in the deep halo, silently circling. We have now traveled so far out that the entire Milky Way galaxy fits within our field of view. It is a splendid island of light in the cosmic dark. We notice that the galaxy is not isolated. In the distance, we see a few small companion galaxies. Two of them, irregularly shaped and pale, cling near the Milky Way. These are the satellite galaxies, the large and small Magellanic Clouds, though we won't name them here. They are like fluttering moths caught in the gravity of a flame, orbiting our galaxy, and in time perhaps to be absorbed by it. Indeed, streams of stars, tidal streams, can be seen tenuously connecting or encircling the Milky Way, marking where past satellite galaxies were torn apart and incorporated. A bit farther out, we spy a great spiral galaxy, not too unlike our own, but slightly larger. The Milky Way's big sister, the Andromeda Galaxy. Even from our vantage, separated by millions of light years, Andromeda's spiral form is discernible, and its light is a fuzzy patch. We realize that our galaxy and Andromeda are on a slow collision course. In several billion years, these two spirals will fall together, intermixing their stars in a grand embrace. The thought is humbling. The stately pinwheel of the Milky Way, which we just admired, is not a permanent fixture, but part of a dynamic dance of galaxies. Now we drift further out, leaving the immediate vicinity of the Milky Way. We enter intergalactic space, an even more profound emptiness, if such a thing is possible. The distances between galaxies are on the order of millions of light years. The Milky Way shrinks behind us, now just one of countless fuzzy specks in a vast, dark cosmos. As we travel, the pattern of the cosmic web begins to emerge on the largest scales. Galaxies are not scattered randomly. They collect into filaments and clusters. We approach a filament of galaxies, a linear arrangement of many galaxies bound by their mutual gravity and the underlying scaffolding of dark matter. These galaxies are like pearls on a cosmic string, lining up along the filament's length. The filament connects nodes where galaxy clusters reside,
enormous congregations of dozens to hundreds of galaxies swarming around a common center. We venture near one such galaxy cluster. Here, the space between galaxies is still vast, but relatively speaking, the galaxies are much closer together than in quiet regions, like where our Milky Way lives. In clusters, galaxies frequently interact and collide. We witness a galactic collision in progress. Two spiral galaxies within the cluster have drawn near each other, their mutual gravity stretching out long tidal tails of stars and gas. Over hundreds of millions of years, which we cannot observe in real time, but we know from simulations and snapshots at different stages, these galaxies will merge. When they do, their spiral structures will be destroyed, and they may form a single large elliptical galaxy, the kind of big, ball-shaped galaxy often found in cluster centers. Indeed, at the core of this cluster, we see a giant elliptical galaxy dominating its companions, a pile of stars likely formed from many past mergers, now a reddish, sprawling system with little gas left to form new stars. It's essentially a galactic city that has grown by consuming neighbors. All around in this cluster, galaxies orbit and interact. Some are spirals with distorted arms from past close encounters. Some are smaller dwarf galaxies, drawn inexorably toward the giants. Clouds of hot gas fill the cluster, undetectable to our eyes, but glowing in X-rays. Gas that has been stripped from galaxies during collisions and now enriches the intergalactic medium with heavy elements forged in stars. The cluster is a crucible of change for galaxies, a place where they evolve rapidly through interactions. Beyond this one cluster, we recognize that it is part of a larger pattern, a supercluster of galaxies linked by filaments. And between these filaments and clusters lie the voids, truly vast regions, tens of millions of light years across, that contain hardly any galaxies at all. These voids are like enormous black cavities, cosmic deserts separating the lush oases of galaxy clusters and filaments. By volume, the voids dominate the universe, yet they are dark and practically empty. Most of the universe is space, just space, with only trace particles and a few stray atoms wandering over unimaginable expanses. We pause in our journey now and take in the panorama of the cosmos. Everywhere we look, there are galaxies upon galaxies. The numbers defy grasp. To give a sense, if you held a grain of sand at arm's length and looked at the patch of sky it covered, that tiny patch could contain thousands of galaxies visible to the most powerful telescopes. There is no empty spot in the sky if your eyes are sensitive enough. Every direction is filled with the faint glow of distant galaxies. Scattered across the darkness like glittering jewels on black velvet, galaxies appear in all shapes and sizes. Elegant spirals, round ellipticals, irregular blobby ones distorted by gravitational encounters, tiny dwarf galaxies barely distinguishable from star clusters. We realize now that our Milky Way is just one of billions, in fact, hundreds of billions or more, of galaxies in the observable universe. Standing here in the gulf between clusters, with galaxies surrounding us in every direction, the scale is staggering. Each galaxy, containing billions or trillions of stars, is itself a universe of possibilities, and there are countless such galaxies. We reflect on the scale of it all. Our entire solar system is an invisible speck. The Earth would be utterly indiscernible, lost in the glare of the sun, which itself is just one modest star in the Milky Way. And the Milky Way is one galaxy among uncounted multitudes stretching for billions of light years in every direction. The light from the most distant galaxies we can see has traveled for over 10 billion years to reach us. We are literally looking into the deep past when we look far away. Light is a time machine. Every photon carries the story of the distance it has traveled. A star 200 light years away shines to us with light that left it 2 centuries ago, around the time of Beethoven and Napoleon on Earth. A galaxy 200 million light years away sends us light that departed when dinosaurs still walked our planet. The farther we gaze, the earlier in time we see.
This is one of the universe's great truths. Distance is time. As we observe galaxies billions of light years away, we are seeing them as they were billions of years in the past. The universe at that time was younger, and indeed, those far-flung galaxies appear smaller, more irregular, and often blue with fierce star formation. They are the adolescent galaxies of a younger cosmos, still growing and colliding more frequently. Their shapes are often clumpy or peculiar. Some are in the midst of mergers or rapid starbursts. We are, effectively, watching the universe grow up as we look farther out and back in time. Approaching the horizon of the observable universe, we see the faint glimmers of the first galaxies that formed. They are tiny proto-galaxies, just beginning to coalesce. Their light has traveled almost the entire age of the universe to reach this vantage point. Beyond them, eventually, we reach a point where galaxies did not yet exist. The universe was too young and too hot. If we look beyond even the earliest galaxies, we encounter a glow that comes from all around us. Not from stars or galaxies, but from the universe itself when it was just a baby. This is the cosmic microwave background, the remnant light from the birth of the cosmos. When the universe was about 380,000 years old, infinitesimal compared to its current age of 13.8 billion years, it was a hot, dense plasma of particles and light. As it expanded and cooled, it became transparent, and light was set free to travel. That first light, a blaze of white-hot radiation at the time, has been traveling for almost 14 billion years, stretching and cooling with the expansion of space, and has now become a faint microwave glow coming from every direction. We cannot see it with our eyes, but if we had microwave vision, the entire sky would glow with a gentle cold fire of creation, about 2.7 degrees above absolute zero. These are the most ancient photons, the universe's own afterglow. Embedded in that diffuse glow are tiny ripples, the seeds that would later grow into galaxies and clusters under gravity. We are essentially beholding the cosmic dawn. Beyond this wall of light, the universe was opaque and no light escapes from earlier times. It is the ultimate limit of the observable. Here, at the edge of all we can see, we stop. We are floating in the darkness between galaxy clusters, with the light of billions of years and billions of galaxies surrounding us. We have traveled from the blue skies of Earth to the edge of the universe's visibility. Time and space have been our companions. We have seen the universe in its youth and at its grandest scales. It is time to go home. Gently, we turn our perspective and begin the long journey back inward. Like a camera pulling out of a vast landscape and then zooming in elsewhere, we now retrace our steps. The cosmic web of filaments and voids lies before us like the structure of a great cosmic sponge. We locate the particular filament where our local group of galaxies, the small cluster containing the Milky Way and Andromeda, among others, resides. Moving along that filament, we pass by cluster after cluster, each a swarm of galaxies, until we recognize the slightly quieter neighborhood of our home supercluster. We find the familiar face of the Milky Way galaxy again among its companions. As we draw nearer, the other galaxies of the local group spread out around us. Andromeda, with its spiral arms, the Magellanic Clouds hovering near our Milky Way. We plunge back toward the Milky Way. From above, we see its spiral arms and bar grow larger, filling our view. We angle downward and descend into the disk, like a cosmic diver slipping into a rotating sea of stars. We pass through the stellar halo, whizzing by an ancient globular cluster whose densely packed stars surround us momentarily, like a blizzard of golden snow, before receding into the background. We cross the boundary of the thick disk, where the star density increases. Soon, we are once again amidst the familiar cloudy band of the Milky Way's disk. Star clusters and nebulae dot the scene. The light around us becomes a continuous ocean of stars.
the backdrop of the Milky Way that we see as the Milky Band in Earth's sky.
We know our sun lies in a quiet region on the inner edge of a spur between the Sagittarius and Perseus spiral arms. We navigate by recognizing nearby stellar landmarks. There is a particular open cluster of young blue stars, the Pleiades perhaps, or another known cluster. A signpost that we are near the Orion arm. We slip into our sun's local stellar neighborhood. The pattern of familiar constellations gradually reassembles around us, though from our still somewhat removed perspective, they appear slightly out of shape. As we draw within a few dozen light years, the constellations snap back to their familiar look. There, ahead, a yellow star glows with a steady, comforting light. It is average in mass and brightness, unremarkable among the many here, but to us, it is unmistakable: the Sun. Approaching the Sun, we begin to see its family of planets in orbit. The outer planets greet us first. Neptune, a tiny turquoise dot with a faint ring system. Uranus, tilted on its side, a pale green-blue orb. Then the majestic Saturn, encircled by its splendid rings, shining in reflected sunlight. We pass by Saturn's domain, catching a last glimpse of the shadow its rings cast on the planet's cloud tops. Soon Jupiter looms, the giant, with its swirling bands and great red spot coming into view. Perhaps as we sweep past it, we watch one of its large moons casting a black round shadow on Jupiter's cloud surface, a tiny eclipse in progress. We leave Jupiter behind and continue inward, crossing the asteroid belt, still as mostly empty as before. Now the inner solar system unfolds. Mars, glowing faintly red with its deserts and canyons, marks the outer edge of the comfortable zone around the Sun. We skim past Mars, maybe glimpsing the white sparkle of its polar ice cap and the dark stain of an ancient volcanic plateau. Ahead, the Earth appears, a brightening bluish star next to the Sun. As we draw closer, it resolves into a delicate crescent, then a half-lit globe, then nearly full. We watch the Moon, now a familiar companion, orbiting around the Earth, the pair shining together in the sunlight. How vibrant the Earth looks against the black of space. From out here, one can see the blue of its oceans and the white of its clouds swirls clearly. The continents show as golden green patches. Perhaps it is night on the side facing us. If so, we see the night side sprinkled with the lights of human cities, a golden web across the dark land, shimmering and blinking with life and activity. Perhaps thunderstorms dot the tropical night, flashing silently as they did when we watched from low Earth orbit. The thin atmospheric halo encircles the Earth's circumference, a fragile glowing line that reminds us how tenuous the boundary between Earth and space is. We descend toward Earth. The blue planet grows until it dominates our view, stunning in its beauty. We slide into the upper atmosphere once more, watching the stars fade behind a growing haze of scattered light. The sky turns from black to deep purple to blue. We feel a gentle tug, the pull of gravity, which never truly left us, but was negligible for so long, now asserts itself as we slow down. Rushing through high, thin air, wisps of clouds racing past, we experience a welcome return of sound, a faint whistle that builds to a roar as the atmosphere embraces us. Parachuting down in our mind's eye, we drift through the tropospheric clouds. Perhaps it is dawn in the place we descend. The horizon is aflame with rosy light, and the shadow of night is retreating westward. Below, the Earth's surface comes into focus, the outlines of coasts, the gleam of sunlight on water, the rich greens of forests or browns of mountains. With a gentle landing, we set foot on the Earth once more. The ground is solid and familiar. We inhale. The air fills our lungs, full of oxygen that plants have made, and we exhale, returning carbon dioxide to the biosphere. In that single breath are also traces of the cosmos, a few atoms of argon that have been part of Earth's air for eons,
and even a few ancient photons from the cosmic microwave background, which our lungs do not filter out. Above, the sky is blue and bright, concealing the stars we visited. The sun shines warmly, and cottony clouds drift in a gentle breeze. Birds might be singing, or a child laughing somewhere, the sweet, ordinary sounds of home that were absent in the mute vacuum of space. Standing here, we reflect on the journey. We traveled from the small, our fragile atmosphere at the edge of space, to the immeasurably large, the cosmic web of galaxies. We experienced the birth of stars in nurseries of gas, and the death of stars in supernova remnants and white dwarfs and neutron stars. Though unseen, they were there in the tapestry. We saw planets adrift without suns, and suns adrift in the gulf between galaxies. We saw that the universe has structure grander than any story ever told, yet it's governed by simple forces that bind atoms into molecules, molecules into dust, dust into planets, planets around stars, stars into galaxies, galaxies into clusters, a hierarchy of connections, an order in the chaos. And most profoundly, we realize that we are part of this story. The atoms that compose our bodies were forged in those distant stars. The iron in our blood, the calcium in our bones, the carbon in our muscles, the oxygen in our lungs, those atoms were brewed in the hearts of ancient stars and scattered through space by stellar winds and supernovae, Amn-Org. They drifted through the galaxy, became part of the cloud that formed the sun and earth, and ultimately became us. We are literally made of star stuff. We carry inside us a piece of the cosmos's history. Every breath we take links us to the cosmic past, inhaling argon atoms exhaled by dinosaurs and photons that have been traveling since the dawn of time. When we look up at the night sky, the same sky we saw from orbit as a thin glow and from the galactic outskirts as a band of light, we are not looking into a foreign realm. We are looking into our own origins. The water in our veins was perhaps once ice in an interstellar cloud. The proteins that make our skin incorporate nitrogen and sulfur cooked up in supernovae. The light in our eyes as we gaze upward is only made possible by the sun, which itself is a second-generation star, enriched by earlier stars' gifts. Indeed, the very awareness with which we contemplate the universe is a product of the universe itself. Over billions of years, it has evolved the capacity to see and wonder about itself through us. In a profound sense, we are a way for the cosmos to know itself. Our journey outward and back has been at once humbling and elevating. We felt insignificant in the face of galaxies and voids, and yet we also felt transcendent, able to encompass in mind what is physically untraversable in body. Floating in the intergalactic dark, we felt small. But standing here on Earth, we can close our eyes and recall the entire sweep of the cosmos that we have imagined, and realize that in some way, it is contained within us, in our memories, in our consciousness, in the atoms of our bodies that were born out there. Looking around now at the trees, the rocks, and the sky, everything appears as it was, comfortably familiar. And yet, we carry a new perspective. We can whisper to ourselves, in Walt Whitman's words, that a leaf of grass is no less than the journey work of the stars. We have seen that journey work out in the universe, the stars building heavier elements, the galaxies mixing them, the nebulae and planets forming, all leading to a leaf of grass and to us. Outer space is not distant. It is not merely the domain of astronauts and telescopes. It permeates our world and our being. The space that begins where our atmosphere ends extends unbroken all the way to the farthest galaxy and beyond, and we are part of it, woven from its threads. The void between the stars is also the void between the atoms in our bodies. The light of the Big Bang's afterglow gently bathes the Earth even now. The gravity that guides galaxies holds us firmly on the ground. we are connected intimately to the whole. The boundary between Earth and space is a matter of perspective. From the vantage of the universe, there is no boundary. It is one continuous expanse, and we are inhabitants of it. So when we gaze at a starry night, or marvel at a photo from a space telescope, let's remember, we are home. We have always been home. The stars are our ancestors and our descendants. The immense cosmos is not cold and foreign. It is our larger body, our extended family, our collective story. We arrived from it, we live in it, and we will return to it. In the end, stepping back from our extraordinary voyage, we feel a deep sense of belonging. We stand on Earth, perhaps on a quiet hill under a night sky sprinkled with stars, and we feel both tiny and vast, fragile and powerful. We have journeyed to the edges of reality and back on the wings of understanding and imagination. And what we have learned, more than any specific fact or sight, is a simple truth that fills us with peace. Outer space is not distant. It is everywhere. It is in the air we breathe, the ground we walk, the blood in our veins. Outer space is not just above us, it is within us. Outer space is us.